Scientists have proven that information can travel faster than light, that particles can tunnel through walls, and that the future might actually influence the past. These aren't science fiction fantasies. They're the bizarre realities of quantum mechanics that we'll explore together. Wave-particle duality. In the early years of the 20th century, physicists discovered something that challenged everything they thought they knew about the nature of reality. Light, which had been understood as a wave for over a century, began revealing particle-like properties. Electrons, which everyone assumed were particles, started behaving like waves. This discovery would fundamentally reshape our understanding of matter and energy, leading us into the strange and beautiful world of quantum mechanics. The story begins with a simple observation about hot objects. When you heat a piece of metal, it glows first red, then orange, then white as the temperature increases. This thermal radiation follows predictable patterns, and by the late 1800s, physicists had developed equations to describe how much energy hot objects should emit at different wavelengths. But there was a problem. The classical equations predicted that hot objects should emit infinite amounts of ultraviolet radiation, which clearly didn't happen in reality. Max Planck solved this puzzle in 1900 by proposing something radical. He suggested that energy could only be emitted in discrete chunks or quanta. The size of each quantum was proportional to the frequency of the radiation. This meant that higher frequency radiation, like ultraviolet light, required larger energy jumps, making it less likely to be emitted at lower temperatures. Planck's quantum hypothesis resolved the ultraviolet catastrophe and introduced the fundamental constant that bears his name. But Planck himself wasn't entirely comfortable with his revolutionary idea. He initially thought of quantization as a mathematical trick rather than a fundamental property of nature. It would take Einstein to recognize the deeper implications of Planck's discovery and push the quantum revolution forward. In 1905, Einstein tackled another puzzling phenomenon called the photoelectric effect. When light shines on certain metals, it knocks electrons loose from the surface. But the behavior of these ejected electrons didn't match classical expectations. According to wave theory, brighter light should eject electrons with more energy, since brighter light carries more energy. Instead, experiments showed that the energy of ejected electrons depended only on the color of the light, not its brightness. Einstein explained this by extending Planck's quantum hypothesis to light itself. He proposed that light consists of discrete packets of energy called photons. Each photon carries energy proportional to the light's frequency. When a photon strikes an electron in the metal, it transfers all its energy to that electron in a single collision. This particle-like behavior of light explained why the electron's energy depended on frequency rather than intensity. The implications were staggering. Light, which had been firmly established as a wave phenomenon through countless interference and diffraction experiments, was now showing unmistakable particle properties. The photoelectric effect could only be understood if light came in discrete chunks rather than continuous waves. But the wave nature of light didn't simply disappear. Young's double-slit experiment, performed over a century earlier, had demonstrated light's wave properties through clear interference patterns. When light passes through two closely spaced slits, it creates alternating bright and dark fringes on a screen beyond. This interference pattern can only result from waves adding and cancelling each other out. So light appeared to be both wave and particle, depending on how you looked at it. This strange duality became even more mysterious when physicists began studying individual photons. Even single photons, sent one at a time through a double-slit setup, gradually build up the same interference pattern. This suggests that each photon somehow interferes with itself, as if it passes through both slits simultaneously. The mystery deepened when Louis de Broglie proposed in 1924 that all matter might exhibit wave-particle duality. If light, traditionally understood as a wave, could show particle properties, perhaps particles could show wave properties. De Broglie suggested that every particle has an associated wavelength inversely proportional to its momentum. The smaller and lighter the particle, the more prominent its wave properties would be. This prediction was soon confirmed experimentally. Clinton Davison and Lester Germer fired electrons at a crystal surface and observed diffraction patterns characteristic of waves. The electrons were acting like waves, with wavelengths that matched de Broglie's formula exactly. Similar experiments with neutrons, atoms, and even large molecules have since confirmed that wave-particle duality applies to all matter. These discoveries forced physicists to confront a fundamental question about the nature of reality. Are particles and waves different aspects of the same underlying phenomenon? Or do quantum objects somehow switch between being particles and waves depending on how we observe them? The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg, suggests that quantum objects don't have definite properties until they're measured. Before measurement, an electron exists in a superposition of all possible states. It's not that we don't know whether it's a wave or particle, but rather that it genuinely hasn't decided yet. The act of measurement forces the quantum system to choose a specific state. This interpretation implies that the observer plays a fundamental role in determining physical reality. When we design an experiment to detect particle-like behavior, we see particles. When we look for wave behavior, we see waves. The famous phrase, "we get what we look for," takes on profound meaning in quantum mechanics. Consider the modern version of the double-slit experiment using individual electrons. When both slits remain open and no detector monitors which slit each electron passes through, we observe an interference pattern characteristic of waves. Each electron somehow goes through both slits and interferes with itself. But if we place detectors at the slits to determine which path each electron takes, the interference pattern disappears. The electrons now behave like classical particles, each taking a definite path through one slit or the other. This complementarity, as Bohr called it, means that wave and particle properties are mutually exclusive aspects of quantum reality. We can observe one or the other, but never both simultaneously. The experimental setup itself determines which aspect reveals itself. The uncertainty principle provides another perspective on wave-particle duality. Heisenberg showed that certain pairs of properties, like position and momentum, cannot be measured simultaneously with perfect precision. The more precisely we determine a particle's position, the less we know about its momentum, and vice versa. This isn't a limitation of our measuring instruments, but a fundamental property of quantum reality. Wave-like properties are associated with extended, delocalized states where position is uncertain, but wavelength and frequency are well defined. Particle-like properties correspond to localized states where position is relatively well defined, but momentum becomes uncertain. The uncertainty principle explains why we can observe either wave or particle behavior, but not both aspects clearly at the same time. The mathematics of quantum mechanics captures this duality through the wave function, a complex valued function that contains all available information about a quantum system. The wave function evolves according to the Schrödinger equation, which describes how probability waves propagate through space and time. When we make a measurement, the wave function collapses to give definite values for observable quantities. Modern quantum field theory provides perhaps the deepest understanding of wave-particle duality. In this framework, particles are excitations in underlying quantum fields that permeate all of space. The field itself has wave-like properties, while individual excitations appear as particles. An electron is an excitation in the electron field, a photon is an excitation in the electromagnetic field, and so forth. This field picture explains why the same entity can exhibit both wave and particle properties. The underlying field is wave-like, spreading throughout space and capable of interference and diffraction. But when the field interacts strongly with measuring devices or other systems, it manifests as localized particle-like excitations. Quantum field theory also explains why particles can be created and destroyed in high-energy interactions. Adding energy to a field can create new excitations corresponding to particle creation. Removing energy can cause excitations to disappear, corresponding to particle annihilation. The wave-like fields are permanent features of space-time, but the particle-like excitations can come and go. The technological applications of wave-particle duality have revolutionized modern life. Lasers exploit the wave nature of light to create coherent beams with precise frequencies and phases. Electron microscopes use the wave properties of electrons to achieve much higher resolution than optical microscopes. Quantum electronics, including transistors and computer chips, relies on the quantum mechanical behavior of electrons in semiconductors. Medical imaging techniques like PET scans depend on particle-antiparticle annihilation, while MRI machines use quantum properties of atomic nuclei to create detailed images of soft tissues. Solar cells and LEDs convert between light and electrical energy through quantum mechanical processes that involve both wave and particle aspects of electromagnetic radiation. Recent advances in quantum technology are pushing wave-particle duality into new frontiers. Quantum computers use superposition states that exist simultaneously in multiple configurations, processing information in ways impossible for classical computers. Quantum cryptography exploits the fact that measuring quantum states disturbs them, providing theoretically unbreakable communication security. Single-photon sources and detectors allow researchers to study quantum behavior at the most fundamental level, manipulating individual quanta of light. Atom interferometry uses the wave nature of atoms to make incredibly precise measurements of gravity, rotation, and acceleration. These techniques are opening new possibilities for navigation, geology, and tests of fundamental physics. The philosophical implications of wave-particle duality continue to generate debate and wonder. If fundamental particles don't have definite properties until measured, what does this say about the nature of reality itself? Some interpretations suggest that multiple realities exist simultaneously until observation selects one. Others propose that consciousness plays a fundamental role in collapsing quantum superpositions. These questions extend beyond pure physics into biology, neuroscience, and the study of consciousness. Some researchers investigate whether quantum effects in microtubules within neurons might contribute to consciousness and free will. While these ideas remain speculative, they illustrate how quantum mechanics challenges our basic assumptions about mind and matter. Wave-particle duality teaches us that nature operates according to principles that transcend our everyday experience and intuition. The quantum world doesn't follow the either-or logic of classical physics, but embraces a both-and reality where entities can simultaneously possess seemingly contradictory properties. This duality reflects a deeper truth about the limits of classical concepts when applied to quantum reality. Waves and particles are human constructs, useful models that capture different aspects of quantum behavior but fail to encompass the full richness of quantum phenomena. The quantum world is neither waves nor particles, but something more fundamental that can manifest as either depending on how we choose to observe it. Understanding wave-particle duality requires letting go of our insistence that reality must conform to everyday experience. The quantum world operates according to its own logic, one that embraces uncertainty, superposition, and the fundamental role of observation in determining physical properties. As we continue exploring the quantum realm, wave-particle duality remains one of the most profound and beautiful aspects of nature's design. It reminds us that reality is far stranger and more wonderful than classical physics ever suggested, inviting us to expand our understanding and embrace the mystery at the heart of existence. Quantum entanglement. Deep in the heart of quantum mechanics lies a phenomenon so strange that Albert Einstein called it spooky action at a distance. Quantum entanglement connects particles in ways that seem to defy our understanding of space and time, creating correlations that persist across vast distances and challenge our most basic assumptions about the nature of reality. When two particles become entangled, they form a single quantum system that cannot be described by treating each particle separately. Measuring one particle instantly determines the properties of its partner, regardless of how far apart they may be. This connection transcends the ordinary limits of physical interaction and suggests that the universe operates according to principles far stranger than classical physics ever imagined. The story of entanglement begins with the fundamental mystery of quantum measurement. In quantum mechanics, particles don't possess definite properties like position or spin until they're observed. Before measurement, a particle exists in a superposition of all possible states simultaneously. An electron, for example, can be spinning both clockwise and counterclockwise at the same time, only choosing a definite direction when someone measures it. This superposition principle becomes even more mysterious when applied to multiple particles. Consider two electrons prepared in a special quantum state where their total spin equals 0. If one electron is spinning up, the other must be spinning down to maintain the 0 total. But in the quantum realm, neither electron has a definite spin direction until measured. Instead, the system exists in a superposition where both electrons are simultaneously spinning up and down. When we measure the first electron and find it spinning up, something remarkable happens. The measurement instantly forces the second electron into the opposite spin state, even if it's located on the other side of the galaxy. The correlation between the particles appears to be established faster than light could travel between them, suggesting some form of instantaneous connection that transcends ordinary spacetime. This instantaneous correlation troubled Einstein deeply. In 1935, he collaborated with Boris Podolsky and Nathan Rosen to formulate what became known as the EPR paradox. They argued that quantum mechanics must be incomplete because it seemed to require faster-than-light communication between distant particles. Einstein believed in local realism, the idea that objects possess definite properties independent of observation and that distant events cannot instantly influence each other. Einstein proposed that entangled particles must carry hidden variables, predetermined instructions that specify how they should behave when measured. In this view, the particles aren't really connected across space, but simply following a script established when they were first created together. The apparent correlation would be like two coins that always land on opposite sides because they were prepared with opposite orientations from the beginning. For decades, the EPR paradox remained a philosophical puzzle without experimental resolution. The hidden variable theory seemed plausible, and the alternative implications of genuine entanglement were so counterintuitive that many physicists preferred Einstein's local realism despite the lack of direct evidence. The breakthrough came in 1964 when physicist John Bell developed a mathematical test that could distinguish between quantum entanglement and hidden variable theories. Bell's theorem showed that certain correlations predicted by quantum mechanics were stronger than any theory based on local hidden variables could produce. If experiments confirmed these strong correlations, it would prove that nature really does exhibit the spooky connections that Einstein found so troubling. Bell's inequalities provided specific numerical bounds that any local realistic theory must respect. Quantum mechanics predicted correlations that would violate these bounds, setting up a crucial experimental test between competing visions of reality. The experiments would need to measure correlations between entangled particles under carefully controlled conditions to see which theory nature actually follows. The first decisive tests were performed by Alain Aspect and his colleagues in the early 1980s. They created pairs of entangled photons and measured their polarizations along different angles. The results clearly violated Bell's inequalities, confirming that quantum mechanics provides the correct description of nature. Subsequent experiments with improved techniques and closed loopholes have consistently supported the quantum mechanical predictions. These experiments proved that either locality or realism must be false. Either distant particles can influence each other instantaneously, or particles don't have definite properties independent of measurement. Most physicists accept that quantum mechanics is correct and that nature is fundamentally non-local, though the particles don't actually send signals to each other faster than light. The resolution lies in understanding that entangled particles don't communicate with each other in any conventional sense. Instead, they share a single quantum state that cannot be decomposed into separate parts. When we measure one particle, we're not changing the other particle, but rather learning about a property of the entire entangled system. The correlation was established when the particles were first entangled, not when the measurement is performed. This interpretation preserves Einstein's relativity by ensuring that no usable information travels faster than light between the particles. While the correlations are instantaneous, they cannot be used to send messages because the measurement results appear random from the perspective of either observer. Only when the observers compare their results do they discover the perfect correlations that reveal the entanglement. The creation of entangled particles requires bringing quantum systems together so they interact and become correlated. One common method involves sending a photon through a special crystal that sometimes splits it into two lower energy photons with correlated properties. Another approach uses atomic systems where electrons can be manipulated with laser pulses to create entangled states. Maintaining entanglement requires protecting the quantum system from environmental interference. Any interaction with the outside world can cause decoherence, destroying the delicate quantum correlations that enable entanglement. This fragility makes entanglement difficult to preserve over long distances or extended time periods, though researchers have developed techniques to combat decoherence and maintain entanglement for practical applications. The degree of entanglement can be quantified using mathematical measures that describe how strongly correlated the particles are. Maximum entanglement occurs when the particles are perfectly correlated, meaning that measuring one completely determines the state of the other. Partial entanglement represents weaker correlations where the particles share some quantum properties but retain some independence. Entanglement can involve more than two particles, creating even more complex quantum correlations. Three-particle entanglement, or tripartite entanglement, exhibits phenomena that cannot be understood by considering any two particles separately. Systems with hundreds or thousands of entangled particles have been created in laboratory settings, though maintaining coherence becomes increasingly challenging as the system size grows. The practical applications of quantum entanglement are revolutionizing technology and opening new possibilities for computation, communication, and sensing. Quantum computers exploit entanglement to process information in ways impossible for classical computers. By creating and manipulating entangled states of quantum bits or qubits, quantum computers can explore multiple solutions simultaneously and solve certain problems exponentially faster than classical approaches. Quantum cryptography uses entanglement to create theoretically unbreakable communication channels. When two parties share entangled particles, they can use the correlations to generate secret keys for encrypting messages. Any attempt to intercept the entangled particles necessarily disturbs them, alerting the communicators to the presence of eavesdropping and ensuring the security of their communication. Quantum teleportation, despite its science fiction name, involves transmitting quantum information rather than physical objects. By combining entanglement with classical communication, researchers can transfer the complete quantum state of one particle to another distant particle. The original particle is destroyed in the process, but its quantum information is perfectly recreated at the destination. Quantum sensing exploits entangled states to make measurements with precision beyond classical limits. Entangled atoms in atomic clocks can achieve timing accuracy that surpasses what's possible with independent atoms. Entangled photons enable enhanced imaging and spectroscopy techniques that can detect extremely weak signals or probe samples with minimal disturbance. The study of entanglement has also revealed deep connections between quantum mechanics and other areas of physics. In quantum field theory, the vacuum itself exhibits entanglement between different regions of space-time. This vacuum entanglement may play a fundamental role in the structure of space-time and could help explain how gravity emerges from quantum mechanical processes. Black hole physics provides another arena where entanglement plays a crucial role. When particles fall into a black hole, they become entangled with the black hole's internal degrees of freedom. As the black hole evaporates through Hawking radiation, these entanglements create complex correlations between the outgoing radiation and the black hole interior that may help resolve the information paradox. Cosmological scenarios also involve entanglement on vast scales. During cosmic inflation in the early universe, quantum fluctuations became stretched across enormous distances while maintaining their entangled correlations. These primordial entanglements may have left observable signatures in the cosmic microwave background radiation and could provide insights into the quantum nature of gravity. The philosophical implications of entanglement continue to generate debate and wonder. If particles can be instantaneously correlated across arbitrary distances, what does this reveal about the fundamental structure of reality? Some interpretations suggest that space and time are emergent properties that arise from more basic entanglement relationships between quantum degrees of freedom. The many worlds interpretation treats entanglement as the mechanism that creates branching realities. When entangled particles are measured, the universal wave function splits into branches corresponding to different measurement outcomes. Each branch contains observers who see consistent results, but the branches become isolated from each other and cannot interact. Other interpretations emphasize the role of information in quantum mechanics. Entanglement represents a form of quantum information that connects distant systems through shared quantum states. This information-theoretic perspective suggests that reality itself might be fundamentally informational rather than consisting of classical matter and energy. Recent research has explored whether consciousness itself might involve quantum entanglement. Some theories propose that entanglement between neurons or other cellular structures could explain the unity of conscious experience and the binding problem in neuroscience. While these ideas remain speculative, they illustrate how entanglement challenges our understanding of mind and matter. The measurement problem in quantum mechanics also connects to entanglement through the process of decoherence. When quantum systems become entangled with their environment, they appear to lose their quantum properties and behave classically. This environmental entanglement might explain how definite measurement outcomes emerge from quantum superpositions without requiring conscious observers or wave function collapse. Entanglement reveals that the quantum world operates according to principles that transcend our everyday intuitions about separability and locality. Objects that seem distinct and independent can share deep quantum connections that persist across space and time. These connections don't violate relativity because they cannot transmit usable information faster than light, but they demonstrate that reality has a fundamentally holistic character at the quantum level. The study of entanglement continues to push the boundaries of physics, technology, and philosophy. As researchers develop better methods for creating, manipulating, and measuring entangled states, they uncover new phenomena and applications that could transform our understanding of information, computation, and the nature of reality itself. Modern experiments routinely create entanglement between different types of particles, including photons, electrons, atoms, and even microscopic mechanical oscillators. These diverse platforms for entanglement enable researchers to explore quantum correlations in different physical contexts and develop applications tailored to specific technological needs. Quantum networks that distribute entanglement between multiple nodes are beginning to emerge as prototypes for future quantum internet infrastructure. These networks could enable distributed quantum computing, where entangled qubits at different locations work together to solve complex problems. They could also support global quantum cryptography networks that provide unprecedented security for sensitive communications. The scaling of entanglement to larger and more complex systems remains an active area of research. Understanding how entanglement behaves in many-body quantum systems could reveal new phases of matter and enable more powerful quantum technologies. Some researchers investigate whether biological systems might exploit entanglement for efficient energy transfer or information processing. Entanglement stands as one of the most profound discoveries in the history of science, revealing connections that transcend our classical understanding of space, time, and causality. It demonstrates that the universe operates according to principles of unity and correlation that extend far beyond what meets the eye. In embracing the reality of quantum entanglement, we open ourselves to a deeper appreciation of the mysterious and interconnected nature of existence itself. Superposition adsorption. At the heart of quantum mechanics lies a principle so fundamental yet so counterintuitive that it challenges everything we think we know about reality. The superposition principle states that quantum systems can exist in multiple states simultaneously, only choosing a definite configuration when observed or measured. This concept forms the foundation of quantum theory and reveals a universe far stranger than our everyday experience suggests. To understand superposition, we must first abandon our classical intuitions about how objects behave. In our macroscopic world, things have definite properties. A coin is either heads or tails, a light switch is either on or off, and a cat is either alive or dead. But in the quantum realm, particles can exist in combinations of these seemingly exclusive states until the moment we observe them. Consider an electron orbiting an atomic nucleus. Classical physics would describe this electron as following a specific path around the nucleus, much like a planet orbiting the sun. But quantum mechanics reveals something far more mysterious. The electron doesn't follow any single path but simultaneously exists in all possible orbital configurations. It's as if the electron is everywhere at once, occupying a cloud of probability that encompasses all the places it might be found. This quantum superposition is not simply a limitation of our knowledge about where the electron actually is. The electron genuinely exists in multiple locations simultaneously until we perform a measurement that forces it to choose a specific position. The act of observation fundamentally changes the nature of the quantum system, collapsing the superposition into a definite state. The mathematical framework of quantum mechanics describes these superposition states using wave functions, complex mathematical objects that encode the probability of finding a particle in any given state. The wave function evolves smoothly and deterministically according to the Schrödinger equation, maintaining superpositions until the moment of measurement causes the wave function to collapse. Superposition extends beyond simple position and applies to all quantum properties. An electron can simultaneously spin clockwise and counterclockwise around its axis. A photon can be polarized in multiple directions at once. An atom can exist in several different energy levels simultaneously. These superpositions create the rich quantum behavior that distinguishes the microscopic world from our everyday experience. The double-slit experiment provides perhaps the most striking demonstration of superposition in action. When individual particles, like electrons or photons, are fired at a barrier containing two slits, they create an interference pattern on the detector screen beyond. This pattern can only arise if each particle somehow passes through both slits simultaneously, interfering with itself to create regions of constructive and destructive interference. Even when we fire particles one at a time, ensuring that each particle is alone in the apparatus, the interference pattern gradually builds up. This proves that superposition is not a collective phenomenon involving multiple particles, but a fundamental property of individual quantum objects. Each particle exists in a superposition of passing through both slits until it strikes the detector and reveals its specific location. The mystery deepens when we attempt to determine which slit each particle passes through. By placing detectors at the slits to monitor the particle's path, we can indeed determine which route each particle takes. But this act of measurement destroys the superposition, and the interference pattern disappears. The particles now behave like classical objects, each taking a definite path through one slit or the other. This reveals a fundamental aspect of superposition. It is fragile and easily destroyed by interaction with the environment. Any measurement or observation that provides information about the system's state causes the superposition to collapse into a definite configuration. This phenomenon, known as wave function collapse, transforms quantum possibilities into classical realities. The collapse of superposition is not gradual but instantaneous and complete. Once a measurement occurs, the quantum system immediately adopts a definite state corresponding to one of the possible outcomes encoded in the original superposition. The other possibilities don't fade away slowly but vanish completely in an instant, leaving behind only the observed result. Schrödinger's cat, perhaps the most famous thought experiment in physics, illustrates the puzzling nature of superposition when applied to macroscopic objects. Imagine a cat sealed in a box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, until we open the box to look, the quantum device exists in a superposition of having triggered and not triggered. This would seem to imply that the cat exists in a superposition of being alive and dead simultaneously. This thought experiment highlights the measurement problem in quantum mechanics. At what point does quantum superposition give way to classical definiteness? Most physicists believe that macroscopic objects like cats cannot maintain quantum superposition because they interact too strongly with their environment. The process of decoherence quickly destroys superpositions in large, complex systems, explaining why we don't observe quantum behavior in everyday objects. Decoherence occurs when a quantum system becomes entangled with its environment. As the system interacts with surrounding particles, radiation, or fields, information about its state spreads throughout the environment. This entanglement effectively measures the system, causing superposition to collapse even without deliberate observation by conscious beings. The time scale for decoherence depends on the size and complexity of the system and its coupling to the environment. Isolated atoms can maintain superposition for extended periods, while larger objects decohere almost instantaneously. This explains why quantum effects become increasingly difficult to observe as we move from microscopic to macroscopic scales. Despite its fragility, superposition enables remarkable phenomena and applications. Quantum computers exploit superposition to process information in fundamentally new ways. While classical bits can only be in states of 0 or 1, quantum bits or qubits can exist in superpositions of both values simultaneously. This allows quantum computers to explore multiple solutions to problems in parallel, potentially providing exponential speedups for certain types of calculations. The power of quantum superposition in computation comes from its ability to encode and process vast amounts of information simultaneously. A system of just a few hundred qubits in superposition could represent more possible states than there are atoms in the observable universe. While maintaining and manipulating such complex superpositions remains technically challenging, the potential for quantum advantage drives intense research and development efforts worldwide. Superposition also enables quantum sensing and metrology applications that surpass classical precision limits. By preparing atoms or other quantum systems in carefully designed superposition states, researchers can detect tiny changes in magnetic fields, gravitational forces, or other physical quantities with extraordinary sensitivity. These quantum sensors have applications ranging from medical imaging to fundamental physics research. Quantum interferometry uses superposition to make precise measurements of distance, time, and acceleration. The LIGO gravitational wave detectors essentially create superpositions of laser light along their kilometer-long arms, enabling them to detect distance changes smaller than 1,000th the width of a proton. Similar techniques are being developed for space-based gravitational wave detection and tests of general relativity. The interpretation of superposition remains one of the most debated topics in quantum mechanics. The Copenhagen interpretation treats superposition as a fundamental aspect of reality, with wave-function collapse occurring upon measurement. The many-worlds interpretation avoids collapse entirely by proposing that all possible outcomes of quantum measurements occur in parallel branches of a branching multiverse. Other interpretations, such as the pilot wave theory, attempt to restore classical realism by proposing that particles have definite properties guided by quantum wave fields. While these interpretations make the same experimental predictions as standard quantum mechanics, they offer different philosophical perspectives on the nature of superposition and quantum reality. Recent advances in quantum technology have enabled increasingly sophisticated manipulations of superposition states. Researchers can now create and control superpositions involving hundreds of atoms, demonstrating quantum behavior on scales that bridge the microscopic and macroscopic worlds. These achievements push the boundaries of where quantum mechanics applies and test our understanding of the quantum to classical transition. Quantum error correction represents another frontier where superposition plays a crucial role. By distributing quantum information across multiple physical qubits in entangled superposition states, researchers can protect against errors and decoherence that would otherwise destroy quantum computations. These techniques may eventually enable large-scale quantum computers that maintain coherent superpositions for extended periods. The study of superposition in complex many-body systems reveals new phases of quantum matter with exotic properties. Quantum spin liquids maintain superpositions of different magnetic configurations even at absolute zero temperature, while topological superconductors support superposition states protected by global geometric properties. These materials could provide robust platforms for quantum information processing. Biological systems may also exploit superposition in ways we are only beginning to understand. Evidence suggests that photosynthesis in plants and bacteria involves quantum superposition states that enable highly efficient energy transfer. Some theories propose that bird navigation, enzyme catalysis, and even consciousness might involve quantum superposition, though these ideas remain highly speculative. The superposition principle reveals that reality operates according to rules that transcend our classical intuitions about definiteness and locality. At the quantum level, possibilities have a tangible existence that influences physical outcomes even before they become actualized through measurement. This suggests that the distinction between potential and actual, between what might be and what is, becomes blurred in fundamental physics. Understanding superposition requires embracing a probabilistic view of nature where uncertainty is not merely epistemic but ontological. The universe doesn't simply hide definite properties from our observation, but genuinely maintains multiple possibilities simultaneously. This represents a radical departure from classical determinism and suggests that indeterminacy is woven into the fabric of reality itself. The superposition principle also highlights the active role of measurement and observation in physics. Unlike classical physics, where measurement simply reveals pre-existing properties, quantum measurement participates in creating the reality it observes. The choice of what to measure and how to measure it influences which aspects of quantum superposition become manifest. This participatory aspect of quantum mechanics has profound implications for our understanding of the relationship between observers and observed systems. Rather than being passive recipients of information about an independent reality, conscious beings become participants in the ongoing process of reality creation through their choices about what questions to ask of nature. Modern quantum field theory extends superposition to the level of fundamental fields that permeate all of space. Even the vacuum is not empty but consists of quantum field fluctuations that exist in superpositions of different particle configurations. Virtual particles constantly appear and disappear in these vacuum superpositions, contributing to physical phenomena like the Casimir effect and the anomalous magnetic moment of electrons. The superposition principle thus reveals a universe that is far more fluid, interconnected, and participatory than classical physics ever suggested. It shows us a reality where possibilities have genuine physical significance, where measurement creates rather than merely reveals truth, and where the boundary between observer and observed becomes fundamentally ambiguous. As we continue to explore the implications of quantum superposition through advancing technology and deepening theoretical understanding, we uncover new layers of mystery about the nature of existence itself. Superposition stands as a testament to the universe's capacity to surprise us, reminding us that reality is far stranger and more beautiful than our everyday experience could ever suggest. In embracing superposition, we open ourselves to a more profound appreciation of the quantum foundations that underlie all physical phenomena and perhaps consciousness itself. Quantum field theory. Quantum field theory represents one of the most profound shifts in our understanding of reality since Newton first described the laws of motion. This framework abandons the familiar picture of particles moving through empty space and replaces it with something far more fundamental: fields that permeate every point in the universe, with particles emerging as excitations in these underlying fields. To grasp this revolutionary perspective, imagine the surface of a calm lake. The water itself represents a field, extending continuously across the entire surface. When you drop a stone into the lake, ripples spread outward from the point of impact. These ripples are excitations of the water field, temporary disturbances that carry energy and momentum as they propagate across the surface. In quantum field theory, particles are like those ripples. An electron is an excitation in the electron field, a photon is an excitation in the electromagnetic field, and every other particle corresponds to excitations in its respective field. These fields exist everywhere in space, even in regions we consider empty. What we perceive as empty vacuum is actually a seething ocean of quantum fields in their lowest energy states. This field picture emerged from attempts to reconcile quantum mechanics with special relativity. Early quantum mechanics successfully described atoms and molecules, but failed when applied to high-speed particles or processes involving particle creation and annihilation. The problem was that traditional quantum mechanics treated particles as discrete objects moving through a fixed background of space and time. Paul Dirac took the first crucial step by developing a relativistic equation for electrons. The Dirac equation not only described electron behavior at high speeds, but also predicted the existence of antimatter. When Dirac's equation was solved, it yielded solutions with negative energy that initially seemed unphysical. Dirac proposed that these negative energy states corresponded to antiparticles, particles with opposite charge but identical mass. This prediction was dramatically confirmed with the discovery of the positron, the electron's antiparticle, in cosmic ray experiments. The existence of antimatter demonstrated that particles could be created and destroyed, a phenomenon that couldn't be accommodated within the framework of ordinary quantum mechanics, but emerged naturally from relativistic field theory. The development of quantum electrodynamics, or QED, marked the birth of modern quantum field theory. This theory treats the electromagnetic field as a quantum mechanical system, with photons as the quanta of electromagnetic radiation. In QED, the interaction between charged particles occurs through the exchange of virtual photons, messenger particles that pop in and out of existence to carry forces between charges. Virtual particles represent one of the most counterintuitive aspects of quantum field theory. These particles don't satisfy the normal relationship between energy and momentum that real particles must obey. They can travel faster or slower than light, exist for impossibly brief times, and carry energy borrowed from the quantum vacuum. While virtual particles cannot be directly observed, their effects are measurable and form the foundation of all quantum field interactions. The quantum vacuum, far from being empty space, teems with virtual particle activity. Particle-antiparticle pairs constantly appear and disappear in accordance with the uncertainty principle, which allows energy to be borrowed from nothing for brief periods. These vacuum fluctuations have measurable consequences, such as the Casimir effect, where parallel metal plates in vacuum experience a small attractive force due to the difference in virtual particle density between the plates and the surrounding space. Renormalization represents one of the most technically sophisticated aspects of quantum field theory. When physicists calculate interaction probabilities in QED, they often encounter infinite results that seem to make no physical sense. Renormalization provides a systematic procedure for removing these infinities while preserving the theory's predictive power. The key insight behind renormalization is that quantum field theories are effective descriptions valid only up to certain energy scales. The infinities arise when we push the theory beyond its domain of validity. By carefully subtracting these infinities and redefining physical parameters like charge and mass, physicists can extract finite, measurable predictions that agree with experiment to extraordinary precision. The success of QED inspired the development of quantum field theories for the other fundamental forces. Quantum chromodynamics, or QCD, describes the strong force that binds quarks together inside protons and neutrons. Unlike QED, where the force becomes weaker at short distances, QCD exhibits the peculiar property of asymptotic freedom. The strong force actually becomes weaker when quarks are very close together and stronger when they're pulled apart. This behavior explains why quarks are confined within hadrons like protons and neutrons. As quarks are separated, the energy stored in the strong force field between them grows without limit. Eventually, this energy becomes sufficient to create new quark-antiquark pairs, making it impossible to isolate individual quarks. This confinement property makes QCD fundamentally different from electromagnetism and poses unique challenges for theoretical calculations. The electroweak theory unifies electromagnetism with the weak nuclear force responsible for radioactive decay. This theory revealed that these apparently different forces are actually aspects of a single electroweak interaction at high energies. At lower energies, spontaneous symmetry breaking causes the unified electroweak force to split into the familiar electromagnetic and weak forces we observe in everyday phenomena. The Higgs mechanism provides the theoretical framework for understanding how particles acquire mass through interaction with the Higgs field. This field permeates all of space and has a non-zero value even in its ground state. Particles that interact strongly with the Higgs field become massive, while those that don't interact with it remain massless, like photons. The discovery of the Higgs boson at the Large Hadron Collider confirmed the existence of the Higgs field and completed the standard model of particle physics. This achievement represented a triumph of quantum field theory, validating theoretical predictions made decades earlier through purely mathematical reasoning. The standard model represents the culmination of quantum field theory applied to fundamental particles and forces. It describes all known elementary particles and 3 of the 4 fundamental forces through a unified framework based on gauge symmetries. Each force corresponds to a particular symmetry of the underlying field equations, and the force-carrying particles arise as gauge fields that maintain these symmetries. Despite its remarkable success, the standard model has significant limitations. It doesn't include gravity, doesn't explain dark matter or dark energy, and contains numerous arbitrary parameters that must be determined experimentally. These limitations suggest that the standard model is itself an effective theory that will eventually be superseded by a more fundamental framework. Attempts to extend quantum field theory beyond the standard model include supersymmetry, extra dimensions, and grand unified theories. Supersymmetry proposes that every particle has a superpartner with opposite spin statistics, potentially explaining the hierarchy problem and providing dark matter candidates. Extra-dimensional theories suggest that space has more than 3 dimensions, with the additional dimensions compactified or accessible only to gravity. Grand unified theories attempt to merge the strong, weak, and electromagnetic forces into a single framework at very high energies. These theories predict that the force constants should converge at the unification scale and that protons should decay with extremely long lifetimes. While proton decay has never been observed, the search continues in underground laboratories around the world. Quantum field theory in curved spacetime extends the framework to include gravitational effects. While a complete quantum theory of gravity remains elusive, physicists can study quantum fields propagating in curved spacetime backgrounds. This approach led to the prediction of Hawking radiation from black holes and insights into the thermodynamic properties of horizons. The information paradox in black hole physics arises from the apparent conflict between quantum field theory and general relativity. Quantum mechanics demands that information be conserved in all physical processes, but black holes seem to destroy information when they evaporate through Hawking radiation. Resolving this paradox may require fundamental changes to our understanding of space-time and quantum field theory. Effective field theory provides a powerful framework for dealing with physical phenomena at different energy scales. Rather than seeking a single theory that describes all physics, effective field theory recognizes that different scales may require different descriptions. The Standard Model itself is likely an effective theory that emerges from more fundamental physics at higher energies. This hierarchical view of physics suggests that quantum field theory may not be the final answer, but rather another step in our evolving understanding of nature. String theory represents one attempt to find a more fundamental framework that could encompass quantum field theory as a low energy limit. Other approaches include loop quantum gravity and causal set theory. The applications of quantum field theory extend far beyond fundamental physics. Condensed matter physicists use field-theoretic methods to understand phase transitions, superconductivity, and quantum Hall effects. Many body systems of electrons in solids can be described using techniques borrowed directly from particle physics, revealing deep connections between seemingly unrelated phenomena. Quantum field theory also provides the theoretical foundation for emerging technologies. Quantum computers rely on field-theoretic descriptions of coupled qubit systems, while quantum sensors exploit the properties of quantum fields to achieve unprecedented precision. The development of quantum communication protocols and cryptography systems depends on understanding how information is encoded and transmitted through quantum fields. The conceptual implications of quantum field theory are profound. It suggests that what we perceive as solid matter is actually patterns of excitation in underlying fields. The distinction between particles and empty space becomes blurred, replaced by a picture of reality as field fluctuations in various states of excitation. This view challenges our basic notions of substance and void, suggesting that the universe is fundamentally made of relationships and processes rather than things. The measurement problem in quantum field theory extends the puzzles of ordinary quantum mechanics to relativistic settings. When field excitations are detected, how does the measurement process cause the quantum field to assume definite values? The problem becomes more complex in field theory because measurement events can be space-like separated, raising questions about causality and the simultaneity of collapse events. Virtual particles and vacuum fluctuations raise philosophical questions about the nature of existence and reality. If virtual particles cannot be directly observed but have measurable effects, what does it mean for something to exist? The quantum vacuum filled with virtual activity suggests that nothingness itself has structure and properties, challenging our basic categories of being and non-being. The role of symmetry in quantum field theory reveals deep connections between mathematical beauty and physical truth. The most successful field theories are based on elegant symmetry principles, suggesting that aesthetic considerations may guide us toward fundamental truths about nature. This connection between mathematics and physics continues to inspire theoretical developments and shape our search for more complete theories. Anomalies in quantum field theory, where quantum corrections break classical symmetries, often signal deep physical insights rather than theoretical failures. The chiral anomaly explains why certain particles decay in ways forbidden by classical conservation laws, while gravitational anomalies provide clues about the structure of quantum gravity. These anomalies remind us that quantum field theory continues to reveal surprises about the nature of reality. As our understanding of quantum field theory deepens through advancing computational techniques and experimental precision, we uncover new layers of complexity and beauty in the field theoretic description of nature. The theory continues to evolve, incorporating new mathematical tools and physical insights while maintaining its status as the most successful framework for describing the fundamental constituents and interactions of matter and energy. Quantum field theory stands as one of humanity's greatest intellectual achievements, providing a unified framework for understanding phenomena ranging from the behavior of elementary particles to the structure of vacuum itself. It reveals a universe far richer and more interconnected than our everyday experience suggests, where particles and fields, matter and empty space, existence and non-existence blend together in the quantum dance that underlies all physical reality. The measurement problem. At the heart of quantum mechanics lies a puzzle so fundamental that it challenges our most basic assumptions about reality, observation, and the nature of physical existence. The measurement problem asks a deceptively simple question. How and why do quantum systems transition from existing in multiple states simultaneously to exhibiting single, definite properties when we observe them? In the quantum realm, particles don't possess definite characteristics until they're measured. An electron doesn't have a specific location or momentum, a photon doesn't have a definite polarization, and an atom doesn't occupy a particular energy level. Instead, these systems exist in quantum superpositions, simultaneously embodying all possible states with different probabilities assigned to each possibility. This superposition principle works beautifully in isolated quantum systems. The mathematics of quantum mechanics, governed by the Schrödinger equation, describes how these probability waves evolve smoothly and predictably through time. The wave function, which encodes all possible information about a quantum system, maintains its coherent superposition indefinitely as long as the system remains undisturbed. The problem arises when we try to observe these quantum systems. The moment we perform a measurement, something dramatic happens. The smooth, deterministic evolution of the wave function suddenly stops, and the system instantaneously adopts one specific state from among all the possibilities encoded in the superposition. This transition, known as wave function collapse, appears to violate the very equations that govern quantum evolution. Consider a simple example, an electron with spin that can point either up or down. Before measurement, quantum mechanics describes this electron as existing in a superposition of both spin states simultaneously. The wave function assigns specific probability amplitudes to each possibility, but the electron genuinely exists in both states until observed. When we measure the spin, we find either up or down with probabilities determined by the wave function, but never a mixture of both. This collapse seems to occur instantaneously and completely. One moment the electron exists in superposition, the next it has a definite spin direction. The measurement doesn't gradually reduce the uncertainty or slowly bias the system toward one outcome. Instead, it causes an immediate and total transformation from quantum possibilities to classical reality. The measurement problem becomes even more perplexing when we consider what constitutes a measurement. In principle, any interaction between a quantum system and its environment could trigger collapse. A photon striking an atom, a cosmic ray passing through a detector, or even thermal fluctuations in the surrounding medium might serve as measurements that destroy quantum superposition. But this raises troubling questions about where to draw the line between quantum and classical behavior. If any interaction can cause collapse, why don't we see quantum superpositions destroyed immediately by environmental interactions? Conversely, if only certain types of interactions count as measurements, what makes them special? The standard formulation of quantum mechanics provides no clear criteria for distinguishing measurements from ordinary physical interactions. The problem deepens when we consider the role of consciousness in quantum measurement. Some interpretations suggest that conscious observation plays a fundamental role in collapsing wave functions. In this view, quantum systems maintain their superpositions until observed by conscious beings, at which point the act of conscious awareness forces the system to adopt a definite state. This consciousness-based interpretation faces immediate difficulties. It implies that the presence or absence of conscious observers determines the fundamental nature of physical reality. Before conscious beings evolved in the universe, would quantum systems have remained in eternal superposition? Can unconscious measuring devices trigger collapse, or do they require conscious interpretation of their readings? The von Neumann-Wigner interpretation explicitly embraces the role of consciousness in quantum measurement. According to this view, the entire measurement chain, from the quantum system through the measuring apparatus to the conscious observer, exists in superposition until the moment of conscious awareness. Only consciousness, with its ability to experience definite mental states, can break the chain of quantum superposition and create classical reality. Critics argue that this interpretation makes physics depend on poorly understood aspects of consciousness and psychology. It suggests that the behavior of electrons and photons somehow depends on the mental states of observers, a conclusion that strikes many physicists as implausible. The interpretation also fails to explain how consciousness differs from other physical processes in its ability to collapse wave functions. The many worlds interpretation offers a radically different resolution to the measurement problem. Instead of wave function collapse, this interpretation proposes that all possible measurement outcomes occur simultaneously in parallel branches of reality. When we measure an electron's spin, the universe splits into two branches, one where we observe spin up and another where we observe spin down. In this view, superposition never actually collapses. The universal wave function continues to evolve according to the Schrödinger equation, maintaining all possibilities simultaneously. What we interpret as collapse is simply our subjective experience of finding ourselves in one particular branch of the multiverse. The other branches continue to exist but become inaccessible to us because they evolve independently. The many worlds interpretation eliminates the arbitrary distinction between quantum evolution and measurement-induced collapse by treating measurement as a purely quantum mechanical process. When a measuring device interacts with a quantum system, they become entangled, creating a superposition of different measurement outcomes correlated with different device states. Conscious observers become entangled with this superposition, experiencing each outcome in a separate branch. This interpretation avoids invoking mysterious collapse mechanisms or special roles for consciousness, but it comes at the cost of accepting an enormous multiplicity of parallel realities. Every quantum measurement creates new branches of the multiverse, leading to an exponentially growing numbers of parallel worlds. Many physicists find this ontological cost too high to accept, preferring interpretations that don't require infinite parallel universes. Decoherence theory provides another approach to the measurement problem by explaining how quantum superpositions effectively disappear through interaction with the environment. When a quantum system becomes entangled with its surroundings, the coherent superposition spreads throughout the environment and becomes practically unobservable. The system appears to adopt definite classical properties, even though it technically remains in superposition. Environmental decoherence occurs rapidly for most quantum systems because they constantly interact with photons, air molecules, thermal fluctuations, and other environmental factors. These interactions entangle the system with countless environmental degrees of freedom, making it effectively impossible to observe quantum interference between different states of the system. Decoherence explains why large, warm objects appear classical, while small, isolated systems can maintain quantum behavior. The timescale for decoherence depends on the system's size, temperature, and coupling to the environment. Atomic scale systems, in carefully controlled conditions, can maintain coherence for seconds or longer, while macroscopic objects decohere almost instantaneously. However, decoherence alone doesn't fully solve the measurement problem because it doesn't explain why we observe particular outcomes rather than others. Decoherence can explain why superpositions become unobservable, but it doesn't address why nature selects specific results from the range of possibilities encoded in the wave function. The consistent histories interpretation attempts to resolve this by treating quantum mechanics as a statistical theory that assigns probabilities to different possible histories rather than predicting single outcomes. In this view, the measurement problem dissolves because quantum mechanics was never supposed to predict specific results, but only statistical patterns across many measurements. Objective collapse theories propose that wave function collapse is a real physical process that occurs spontaneously even without observation. The Ghirardi-Rimini-Weber theory suggests that wave functions undergo spontaneous localization at random times, with collapse rates that increase with system size. This explains why microscopic systems can maintain superposition while macroscopic objects appear classical. These theories modify the Schrödinger equation by adding nonlinear terms that cause spontaneous collapse. The collapse occurs rarely for single particles, but becomes frequent for large collections of particles, naturally explaining the quantum to classical transition without invoking consciousness or measurement. The measurement problem also connects to deeper questions about the nature of physical law and the role of information in physics. Some physicists argue that information, rather than matter or energy, is the fundamental currency of physics. From this perspective, measurement doesn't collapse wave functions but rather creates classical information from quantum information. This information theoretic approach suggests that the measurement problem might be resolved by understanding how different types of information processing lead to different physical behaviors. Classical information, which can be copied and broadcast, creates the definite properties we observe in classical systems. Quantum information, which cannot be copied or cloned, maintains the superpositions characteristic of quantum systems. The Wheeler's participatory universe concept suggests that observation doesn't simply reveal pre-existing properties but actually participates in creating physical reality. In this view, the universe doesn't have definite properties independent of observation but exists as a collection of potential properties that become actualized through measurement. This participatory principle makes observers active participants in the ongoing creation of reality rather than passive recipients of information about an independent world. Recent developments in quantum foundations continue to shed new light on the measurement problem. Quantum Darwinism proposes that classical reality emerges through natural selection processes that favor certain quantum states over others. States that can be reliably copied and broadcasted into the environment become classical, while fragile superposition states remain quantum. The problem remains actively debated because it touches on fundamental questions about the nature of reality, consciousness, and physical law. Different interpretations offer different answers, but none has achieved universal acceptance among physicists. The measurement problem continues to drive research in quantum foundations, inspiring new experiments and theoretical developments. Laboratory tests of different interpretations are increasingly sophisticated, though definitive experiments remain challenging because many interpretations make identical predictions for practically accessible measurements. Tests of spontaneous collapse theories, searches for deviations from quantum mechanics in large systems, and studies of the quantum to classical boundary continue to refine our understanding. The measurement problem illustrates the profound conceptual challenges that arose when physics moved beyond classical determinism into the quantum realm. It shows how our most successful scientific theory contains deep puzzles about the nature of observation, reality, and the relationship between conscious observers and physical systems. Understanding measurement remains crucial for developing quantum technologies that exploit superposition and entanglement while avoiding unwanted collapse. Quantum computers, sensors, and communication systems all depend on controlling when and how quantum measurements occur. The practical demands of quantum technology continue to drive theoretical understanding of measurement processes. The measurement problem ultimately asks us to confront the limits of classical intuition when applied to quantum reality. It suggests that the act of observation might be more fundamental to physics than classical theories assumed, playing an active role in determining the nature of physical reality rather than simply revealing pre-existing facts about the world. As our ability to create and manipulate quantum systems grows more sophisticated, the measurement problem becomes increasingly relevant to understanding how classical reality emerges from quantum foundations. Whether through consciousness, decoherence, many worlds, or spontaneous collapse, the transition from quantum possibility to classical actuality remains one of the deepest mysteries in our understanding of the physical universe. Special relativity. In 1905, a young patent clerk in Bern, Switzerland, published a paper that would fundamentally reshape our understanding of space, time, matter, and energy. Albert Einstein's theory of special relativity emerged from his attempt to reconcile the laws of physics with a puzzling experimental result. Light always travels at the same speed regardless of how the observer moves. This simple observation led to conclusions so counterintuitive that they challenged humanity's most basic assumptions about the nature of reality. The story begins with James Clerk Maxwell's equations describing electromagnetic radiation. These equations predicted that light waves should travel at a specific speed through space, but they raised a troubling question. Speed is always measured relative to something else. A car traveling at 60 miles per hour moves at that speed relative to the road, but appears stationary to a passenger inside. If light has a definite speed, what is it moving relative to? 19th century physicists assumed that light must propagate through an invisible medium called the luminiferous ether that filled all of space. Just as sound waves travel through air, light waves were thought to travel through this ether. The Earth's motion through space should create an ether wind that would affect the speed of light measured in different directions, just as a headwind or tailwind affects the apparent speed of sound. Albert Michelson and Edward Morley designed a precise experiment to detect this ether wind by measuring light speed in perpendicular directions. Their interferometer split a light beam and sent the two parts along paths at right angles to each other before recombining them. If the Earth were moving through the ether, light traveling parallel and perpendicular to the planet's motion should have slightly different travel times, creating a detectable interference pattern. The result was shocking. No matter how they oriented their apparatus or when they performed the measurement, Michelson and Morley found no evidence of ether wind. Traveled at exactly the same speed in all directions, as if the ether didn't exist, or as if the Earth were always stationary relative to it. This null result puzzled physicists for decades and set the stage for Einstein's revolutionary insight. Einstein approached the problem from a different angle. Instead of trying to explain why the ether couldn't be detected, he questioned whether it needed to exist at all. What if the speed of light in vacuum is truly constant, the same for all observers regardless of their motion? This seemingly simple assumption led to profound consequences that transformed our understanding of space and time. The constancy of light speed means that space and time cannot be absolute and independent as Newton had assumed. If light travels at the same speed for all observers, then moving observers must experience space and time differently. The measurements of distance and duration that seem natural and obvious to us are actually relative to our state of motion. Consider two observers, one stationary and one moving at high speed relative to the first. When they both measure the speed of the same light beam, they must get identical results despite their different velocities. Since speed equals distance divided by time, this is only possible if their measurements of distance and time differ in precisely the right way to keep the calculated speed constant. This leads to the phenomenon known as time dilation. Moving clocks run slower compared to stationary ones. A clock carried by a high-speed traveler will tick more slowly when observed by someone at rest. This isn't a mechanical effect caused by motion disturbing the clock's mechanism, but a fundamental property of time itself. All physical processes, from atomic vibrations to biological aging, proceed more slowly for moving observers. The mathematical relationship is elegant and precise. Time dilation depends on the Lorentz factor, which approaches 1 for slow speeds, but grows dramatically as velocity approaches the speed of light. At 90% of light speed, time passes about twice as slowly. At 99% of light speed, time slows by a factor of 7. As speed approaches light speed, time dilation approaches infinity. Length contraction provides the spatial counterpart to time dilation. Objects appear shortened in their direction of motion when observed from a stationary reference frame. A meter stick carried by a high-speed traveler appears less than a meter long to a stationary observer. Like time dilation, this effect becomes negligible at everyday speeds, but dramatic at relativistic velocities. These effects are perfectly reciprocal. Each observer sees the other's clocks running slow and rulers contracted. There's no absolute reference frame that determines who is really moving. Motion is purely relative, and each observer has an equally valid perspective on space and time measurements. The famous twin paradox illustrates the counterintuitive nature of relativistic effects. Imagine identical twins where one remains on Earth while the other travels to a distant star at high speed. During the journey, each twin observes the other's clocks running slowly due to their relative motion. But when the traveling twin returns to Earth, they will have aged less than their Earth-bound sibling. The resolution of this apparent paradox lies in the fact that the traveling twin must accelerate to turn around and return home. This acceleration breaks the symmetry between the twins' experiences and determines who ages less. The twin who experiences acceleration during the turnaround is the one who ages more slowly overall. Experimental confirmation of time dilation and length contraction has been abundant and precise. Atomic clocks flown on airplanes show exactly the time differences predicted by special relativity. Particles created in cosmic ray interactions high in the atmosphere reach Earth's surface because time dilation extends their lifetimes as measured in our reference frame. GPS satellites must correct for relativistic time effects to maintain their accuracy. The relativistic addition of velocities provides another striking departure from classical physics. Speeds don't simply add together as Newton expected. If you're traveling at half the speed of light and fire a projectile forward at half the speed of light, the projectile's speed relative to a stationary observer isn't the speed of light but about 80% of light speed. This velocity addition formula ensures that no material object can exceed the speed of light. As objects approach light speed, additional energy goes into increasing their relativistic mass rather than their velocity. The speed of light represents an absolute cosmic speed limit that cannot be surpassed by accelerating massive objects. Einstein's famous equation E equals mc squared emerges naturally from special relativity. This mass-energy equivalence reveals that mass and energy are different manifestations of the same underlying quantity. Even a stationary object possesses enormous energy by virtue of its mass. The complete energy of a moving object includes both its rest mass energy and its kinetic energy of motion. Mass energy equivalence explains the tremendous energy released in nuclear reactions. When atomic nuclei fuse or split, small amounts of mass convert into large amounts of energy according to Einstein's equation. The sun's power comes from nuclear fusion reactions that convert about 4 million tons of mass into energy every second, demonstrating the practical reality of mass energy conversion. The equation also predicts that accelerating particles to high speeds increases their effective mass. Particle accelerators confirm this prediction daily as they require ever-increasing amounts of energy to accelerate particles to higher speeds. The particles become more massive as they approach light speed, making further acceleration progressively more difficult. Special relativity revolutionized our understanding of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another observer in relative motion. The concept of a universal now that applies throughout the universe doesn't exist in relativity. Different observers slice through space-time differently, creating different definitions of simultaneous events. This relativity of simultaneity emerges from the finite speed of light and the requirement that all observers measure the same light speed. When observers in relative motion synchronize their clocks using light signals, they establish different definitions of simultaneity that depend on their velocity. The geometric interpretation of special relativity treats space and time as components of a four-dimensional space-time continuum. Events are points in this four-dimensional space, and the interval between events is invariant for all observers. What changes between reference frames is how this four-dimensional interval gets divided into spatial and temporal components. Minkowski space-time diagrams provide visual representations of relativistic effects. These diagrams plot space horizontally and time vertically, with light rays traveling at 45-degree angles. The world lines of moving objects appear as curves or straight lines with different slopes, and the geometric relationships in the diagram encode the physics of time, dilation, and length contraction. Special relativity led to the development of relativistic mechanics, electromagnetic theory, and quantum field theory. The requirement that physical laws be the same for all inertial observers constrains the possible forms these laws can take. Many insights in modern physics emerge from applying this principle of relativistic invariance to different physical phenomena. The theory resolved long-standing puzzles about electromagnetic theory by showing that electric and magnetic fields are aspects of a single electromagnetic field that appears different to observers in relative motion. A purely electric field in one reference frame appears as a combination of electric and magnetic fields in another frame moving relative to the first. Relativistic effects become important in many modern technologies. Particle accelerators, nuclear reactors, and medical imaging devices all depend on relativistic physics for their operation. The global positioning system requires relativistic corrections to maintain its accuracy, as the satellite clocks run at different rates due to their motion and their weaker gravitational field. High-energy astrophysics provides dramatic examples of relativistic phenomena. Cosmic rays consist of particles accelerated to nearly light speed by extreme astrophysical processes. Jets of material ejected from black holes and neutron stars travel at relativistic speeds, exhibiting time dilation and relativistic beaming effects observable with modern telescopes. The philosophical implications of special relativity continue to influence our understanding of space, time, and causality. The theory shows that our intuitive notions about simultaneity, duration, and distance are approximations that break down at high speeds. Reality has a structure more subtle and interconnected than everyday experience suggests. Special relativity also established the speed of light as a fundamental constant that plays a central role in the structure of space-time itself. This speed limit affects not just electromagnetic phenomena, but all physical processes, suggesting deep connections between space, time, and the propagation of information and causality. The theory demonstrates how physical principles can lead to unexpected conclusions that challenge common sense. Einstein's willingness to follow logical reasoning to its conclusions, even when they contradicted intuitive expectations, exemplifies the power of theoretical physics to reveal hidden aspects of nature. Special relativity continues to inspire research in fundamental physics, from searches for violations of Lorentz invariance to studies of quantum field theory in accelerated reference frames. The theory remains a cornerstone of modern physics, providing the foundation for particle physics, cosmology, and our ongoing efforts to understand the deepest principles governing the universe. Understanding special relativity requires abandoning absolute notions of space and time, while embracing the counterintuitive reality that motion affects the fundamental measurements of distance and duration. The theory reveals a universe more strange and beautiful than classical physics ever imagined, where space and time form a unified fabric that responds dynamically to the motion of observers and the propagation of light. Black hole information paradox. Black holes present one of the most profound puzzles in modern theoretical physics, challenging our understanding of information, quantum mechanics, and the fundamental nature of space-time itself. The information paradox emerges from a seemingly irreconcilable conflict between two pillars of modern physics: quantum mechanics, which demands that information can never be truly destroyed, and general relativity, which suggests that anything falling into a black hole disappears forever when the black hole eventually evaporates. To understand this paradox, we must first examine what physicists mean by information in this context. Information, in the quantum mechanical sense, refers to the complete specification of a system's quantum state. This includes not just obvious properties like position and momentum, but also subtle quantum characteristics like phase relationships and entanglement correlations. Quantum mechanics treats information as a conserved quantity, meaning it can be scrambled, encoded, or transformed, but never completely erased from the universe. This principle of information conservation, known as unitarity, underlies the reversibility of quantum mechanical processes. In principle, if you knew the exact quantum state of the entire universe at any moment, you could calculate its state at any other time, both forward and backward. This reversibility ensures that the total amount of information in the universe remains constant, even as it becomes redistributed among different systems. Black holes seem to violate this fundamental principle in a dramatic way. When matter falls past a black hole's event horizon, it appears to be lost forever from the perspective of outside observers. Classical general relativity describes the infalling matter as reaching the central singularity, where densities become infinite and the normal laws of physics break down. From this classical viewpoint, the information carried by the infalling matter is simply destroyed. The situation became even more puzzling when Stephen Hawking discovered that black holes are not completely black, but emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate, with smaller black holes evaporating faster than larger ones. Eventually, any black hole will completely disappear, radiating away all of its mass and energy into space. Hawking's original calculation suggested that this radiation is perfectly thermal, meaning it contains no information about what fell into the black hole. Whether you drop a library of books or an equivalent mass of hydrogen gas into a black hole, the resulting Hawking radiation appears identical to outside observers. When the black hole finally evaporates completely, it seems as though the information that fell in has been permanently erased from the universe. This conclusion creates a stark conflict with quantum mechanics. If information falling into black holes is truly destroyed, then the evolution of quantum systems involving black holes cannot be unitary. The implications extend far beyond black hole physics, potentially undermining the mathematical consistency of quantum field theory and our understanding of fundamental physical laws. The paradox became more acute when scientists realized that the conflict involves not just exotic black holes formed from stellar collapse, but any process that creates event horizons. Even microscopic black holes that might be produced in high-energy particle collisions would face the same information paradox. If information can be destroyed in any physical process, it calls into question the foundations of quantum mechanics itself. One proposed resolution involves the concept of black hole complementarity, suggested by Leonard Susskind and others. This approach argues that information falling into a black hole can be described in two different but equivalent ways. From the perspective of an outside observer, the information never actually crosses the event horizon but becomes encoded on the black hole's surface in an increasingly scrambled form. From the perspective of an infalling observer, the information crosses the horizon normally and reaches the interior. According to black hole complementarity, these two descriptions never contradict each other because the outside observer and infalling observer can never compare their experiences directly. By the time the infalling observer could potentially communicate what they observed inside the black hole, they would have been destroyed by tidal forces or the black hole's eventual evaporation. The holographic principle provides another perspective on potential resolutions to the information paradox. This principle suggests that all information contained within a region of space can be encoded on the region's boundary surface. Applied to black holes, this means that everything that falls into a black hole might be encoded on its event horizon rather than being destroyed in the interior. If the holographic principle applies to black holes, then the information falling in becomes part of an increasingly complex pattern on the event horizon surface. As the black hole evaporates through Hawking radiation, this surface information could gradually be released back into the external universe, preserving unitarity even though individual outside observers might not be able to decode the information. However, holographic approaches face their own challenges. The amount of information that can be stored on the event horizon is limited by its surface area, not its volume. This creates puzzles about how large amounts of information can be accommodated as more matter falls into the black hole. Additionally, the mechanisms by which horizon-encoded information gets transferred to outgoing Hawking radiation remain poorly understood. The firewall hypothesis represents a more radical approach to resolving the information paradox. Proposed by Ahmed Almheiri, Donald Marolf, Joseph Polkinski, and James Sully, this solution suggests that maintaining information conservation requires abandoning the smooth passage through the event horizon predicted by general relativity. According to the firewall hypothesis, the event horizon is not an empty region of space, but rather a wall of high-energy particles that would instantly incinerate anything trying to cross it. This firewall preserves information by preventing it from falling into the black hole interior in the first place. Instead, infalling information gets scrambled and encoded in the firewall itself before being gradually released through Hawking radiation. The firewall solution comes at a steep cost. It violates the equivalence principle, one of the fundamental assumptions of general relativity. According to this principle, freely falling observers should not experience any special effects when crossing the event horizon of a large black hole. The firewall hypothesis suggests that this principle fails in black hole spacetimes, requiring modifications to our understanding of gravity. Quantum error correction provides yet another avenue for addressing the information paradox. Recent work has shown that many quantum systems naturally implement error correction protocols that protect information against local perturbations. If black holes and their radiation can be understood as quantum error correcting codes, then information falling into black holes might be protected and recoverable even if it becomes highly scrambled. This approach suggests that the information falling into a black hole gets encoded redundantly across many degrees of freedom in the black hole and its radiation. Local measurements of the Hawking radiation might not reveal this information directly, but sufficiently complex quantum operations on large portions of the radiation could potentially reconstruct the original information. The ADS-CFT correspondence, a concrete realization of the holographic principle, has provided new tools for studying the information paradox. This correspondence relates gravity in the interior of certain spacetimes to quantum field theory on their boundaries. In this framework, black hole formation and evaporation can be studied using the boundary field theory, where unitarity is manifest. Studies using ADS-CFT suggest that information does escape from black holes, but in a highly scrambled form that becomes accessible only after the black hole has evaporated for more than half its lifetime. Before this page time, the Hawking radiation appears thermal and random. After the page time, subtle correlations in the radiation begin to carry information about what fell into the black hole. The emergence of space-time itself from quantum entanglement adds another layer to our understanding of the information paradox. Recent developments suggest that the geometry of space-time might be an emergent phenomenon arising from patterns of entanglement between quantum degrees of freedom. If space and time are not fundamental but rather arise from information processing, then the information paradox might require rethinking our basic concepts about locality and causality. Experimental tests of different resolutions to the information paradox remain challenging because black holes large enough to have long evaporation times are far from laboratory conditions. However, analog systems that simulate aspects of black hole physics in condensed matter or optical systems provide opportunities to study information scrambling and recovery in controlled settings. The black hole information paradox has also stimulated advances in quantum information theory, complexity theory, and our understanding of quantum entanglement. The technical tools developed to address this paradox have found applications in quantum computing, quantum cryptography, and the study of many-body quantum systems. The paradox illuminates deep connections between gravity, thermodynamics, and information theory. Black holes obey thermodynamic laws with their entropy proportional to their surface area and their temperature inversely related to their mass. Understanding how information is encoded and processed in black hole thermodynamics might reveal fundamental principles about the relationship between information and space-time. Some approaches to quantum gravity, such as loop quantum gravity and causal set theory, naturally avoid the information paradox by replacing classical space-time singularities with quantum mechanical processes. In these theories, the extreme conditions near black hole centers are regulated by quantum effects that prevent information from being lost in singularities. The information paradox remains an active area of research, with new insights emerging regularly from advances in quantum gravity, quantum information theory, and holographic duality. While no resolution has achieved universal acceptance, the pursuit of solutions continues to drive fundamental advances in theoretical physics. The paradox serves as a crucial test case for any theory that attempts to unify quantum mechanics with general relativity. Any successful theory of quantum gravity must explain how information behaves in the presence of strong gravitational fields and event horizons. The information paradox thus provides essential guidance for the development of more complete theories of fundamental physics. Recent developments have focused on understanding the precise mechanisms by which information might escape from black holes and the timescales involved in this process. The interplay between quantum error correction, holographic duality, and emergent space-time continues to reveal new aspects of how information and gravity interact at the most fundamental level. The black hole information paradox exemplifies how apparent contradictions in physics can drive revolutionary advances in our understanding. By forcing physicists to confront the limits of established theories, the paradox has opened new avenues of research that may ultimately lead to a more complete understanding of space, time, information, and the quantum nature of gravity itself. The resolution of this paradox, when it comes, promises to transform our understanding of the deepest principles governing the universe. Wormholes and Einstein-Rosen bridges. Deep within Einstein's equations of general relativity lies the possibility of structures so exotic they seem to belong in science fiction rather than serious physics. Wormholes, also known as Einstein-Rosen bridges, represent theoretical tunnels through space-time that could potentially connect distant regions of the universe or even entirely separate universes. These mathematical constructs emerge naturally from the geometry of curved space-time, yet their physical reality remains one of the most speculative and contentious topics in theoretical physics. The concept of wormholes arose from attempts to understand the complete geometry of black holes. When Karl Schwarzschild first solved Einstein's field equations for a spherically symmetric mass, he discovered not just the familiar black hole exterior, but also a complete space-time geometry that extends beyond the event horizon. This complete Schwarzschild solution describes what mathematicians call a maximally extended black hole, containing regions that external observers can never access. The geometry of this extended solution resembles two separate universes connected by a narrow bridge through a higher dimensional space. Picture 2, flat sheets of paper representing different regions of space-time, connected by a tube that passes through a third dimension. This tube represents the wormhole throat, while the two sheets represent the separate space-time regions that the wormhole connects. Einstein and Nathan Rosen studied this geometry in 1935, hoping to use it as a model for elementary particles. They imagined that particles might be manifestations of these bridges in space-time rather than point-like objects embedded in space-time. Though this particular application didn't succeed, their work established the mathematical foundation for understanding wormhole geometries within general relativity. The Einstein-Rosen bridge represents the simplest type of wormhole, connecting two identical black hole exteriors through a throat that exists behind both event horizons. However, this bridge faces a fundamental problem. It's dynamically unstable. The throat of the wormhole collapses so quickly that nothing can traverse it. Any attempt to send matter or even light through the bridge fails because the throat pinches off before anything can complete the journey. This instability arises from the focusing effect of gravity on the wormhole throat. As space-time curves inward to form the bridge, tidal forces naturally compress the throat until it collapses completely. The mathematics shows that this collapse occurs faster than light can travel through the wormhole, making traversal impossible, even in principle. To create a stable, traversable wormhole, physicists realized they would need to introduce exotic matter with unusual properties. Specifically, the wormhole throat must be threaded with matter that has negative energy density, violating what physicists call the null energy condition. This exotic matter would generate repulsive gravitational effects that counteract the natural tendency of the throat to collapse. The required exotic matter would need properties unlike anything observed in nature. While ordinary matter and energy always have positive energy density and create attractive gravitational effects, wormhole stabilization requires matter with negative energy density that generates repulsive gravity. The amount of negative energy needed increases with the size of the wormhole throat, requiring enormous quantities of exotic matter for macroscopic wormholes. Quantum field theory provides some hints that such exotic matter might exist, at least in microscopic quantities. The Casimir effect demonstrates that quantum vacuum fluctuations can create regions with negative energy density between closely spaced conducting plates. However, these quantum effects are extremely weak and localized, far from the macroscopic amounts of negative energy needed to stabilize traversable wormholes. Quantum inequalities place fundamental limits on how much negative energy can exist in any region of space-time. These inequalities suggest that large concentrations of negative energy are forbidden by quantum mechanics, making macroscopic wormholes extremely unlikely. The quantum constraints become more severe for larger wormhole throats, effectively ruling out human traversable wormholes based on our current understanding of physics. Despite these challenges, physicists have explored various exotic matter models that might circumvent the quantum inequalities. Some theories propose that cosmic strings, theoretical, one-dimensional defects in space-time, might provide the negative energy needed for wormhole stabilization. Others suggest that quantum effects in curved space-time might produce the required exotic matter under extreme conditions. The Morris Thorne wormhole represents the most studied model of a traversable wormhole. Proposed by Michael Morris and Kip Thorne in 1988, This geometry describes a spherically symmetric wormhole with specific properties designed for safe traversal. The Morris-Thorne model carefully balances the exotic matter distribution to minimize tidal forces and ensure that travelers could survive the journey through the wormhole throat. In the Morris-Thorne geometry, the wormhole appears as a sphere when viewed from either side. Approaching the wormhole, a traveler would see light from the other side of the bridge, creating a window view into the distant region. The journey through the wormhole would involve passing through this sphere and emerging in a different part of space-time, potentially light years away from the starting point. The exotic matter needed for Morris-Thorne wormholes must be distributed in a specific way throughout the throat region. This threading matter creates a repulsive gravitational field that keeps the throat open while minimizing dangerous tidal effects on passing travelers. The precise arrangement requires careful engineering of the stress-energy tensor, making such wormholes highly artificial constructs rather than naturally occurring phenomena. Time travel complications arise when wormholes connect regions of space-time with different coordinate times. If one mouth of a wormhole is accelerated to high speed while the other remains stationary, relativity ensures that the two mouths will experience different rates of time flow. An observer could potentially enter the accelerated mouth and emerge from the stationary mouth at an earlier coordinate time, creating a closed time-like curve. Such time travel scenarios face the grandfather paradox and related causality violations. If someone could travel back in time through a wormhole, they might be able to prevent their own journey, creating logical contradictions. Some physicists argue that quantum effects, or unknown physical principles, must prevent the formation of closed time-like curves, perhaps by destroying wormholes before they can enable time travel. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics conspire to prevent macroscopic time travel. According to this conjecture, quantum fluctuations become infinite near closed time-like curves, destroying any wormhole before it can enable time travel. While unproven, this conjecture represents one attempt to resolve the apparent conflict between general relativity and causality. Microscopic wormholes might exist naturally as quantum fluctuations in the fabric of space-time itself. At the Planck scale, where quantum effects of gravity become important, space-time might foam with tiny wormholes constantly forming and dissolving. These quantum wormholes would be far too small for macroscopic objects to traverse, but they might affect the propagation of particles and fields in subtle ways. Some theories of quantum gravity predict that black holes might be connected by wormholes to distant regions of space-time. When black holes evaporate through Hawking radiation, the information that fell into them might escape through wormhole connections, rather than being lost forever. This speculative idea represents one potential resolution to the black hole information paradox. The holographic principle and ADESTAR CFT correspondence have provided new insights into wormhole physics. In certain theoretical models, quantum entanglement between separated regions creates emergent wormhole geometries in the bulk spacetime. These ER-EPR proposals suggest deep connections between quantum entanglement and spacetime geometry, with wormholes representing the geometric manifestation of quantum correlations. Experimental detection of wormholes remains extraordinarily challenging because of their exotic matter requirements and likely microscopic scales. Hypothetical signatures might include gravitational lensing effects, unusual particle interactions, or modifications to the propagation of electromagnetic radiation. However, no convincing observational evidence for wormholes exists, and most physicists consider them highly speculative phenomena. Laboratory creation of wormholes appears impossible with current technology and understanding of physics. The exotic matter requirements far exceed anything that could be produced artificially, and the quantum inequalities suggest fundamental obstacles to concentrating sufficient negative energy. Even microscopic wormholes would require conditions far beyond current experimental capabilities. Wormholes in cosmology might play roles in theories of inflation and multiverse scenarios. Some models propose that our universe is connected to others through wormhole networks, allowing for exchange of matter and energy between separate cosmic domains. These ideas remain highly speculative and lack observational support, but they illustrate the far-reaching implications of wormhole physics. String theory and other approaches to quantum gravity provide frameworks for studying wormhole physics beyond classical general relativity. In string theory, wormholes might be stabilized by stringy effects rather than exotic matter, though the required conditions remain extreme. Loop quantum gravity and other discrete approaches to space-time might naturally regulate wormhole formation and evolution. The study of wormholes has contributed significantly to our understanding of space-time geometry, causality, and the limits of general relativity. Even if macroscopic traversable wormholes prove impossible, their mathematical study illuminates fundamental aspects of gravity and space-time that might not be accessible through other approaches. Traversable wormhole research has also advanced techniques in mathematical physics and differential geometry. The methods developed for analyzing wormhole stability and exotic matter requirements have found applications in cosmology, black hole physics, and other areas of theoretical physics where strong gravitational fields play important roles. Science fiction has popularized wormholes as convenient devices for interstellar travel and exploration of parallel universes. While these fictional applications remain far from scientific reality, they have inspired public interest in fundamental physics and the nature of space-time. The gap between scientific possibility and fictional portrayal remains enormous, with real wormhole physics involving extreme conditions and exotic matter requirements that seem to preclude practical applications. Current research continues to explore the boundaries of what might be possible with wormhole geometries. Some studies examine whether quantum effects might provide alternative stabilization mechanisms, while others investigate connections between wormholes and fundamental theories of quantum gravity. The intersection of wormhole physics with quantum information theory has opened new avenues for understanding the relationship between space-time geometry and quantum entanglement. The challenges facing wormhole physics illustrate the deep connections between space-time geometry, quantum mechanics, and thermodynamics. The exotic matter requirements for traversable wormholes push against fundamental limits imposed by quantum field theory, while time travel possibilities raise questions about causality and the nature of physical law. Wormholes represent a fascinating intersection between mathematical possibility and physical reality. While Einstein's equations permit their existence in principle, the practical requirements for creating and maintaining stable, traversable wormholes appear to be prohibited by quantum mechanics and thermodynamics. Yet their study continues to provide insights into the deepest aspects of space-time, gravity, and the fundamental limits of what might be possible in our universe. The exploration of wormhole physics reminds us that mathematical consistency doesn't guarantee physical realizability. The elegant geometries described by general relativity must ultimately conform to quantum mechanical constraints and thermodynamic principles. Understanding these boundaries helps define the limits of what's possible while continuing to push the frontiers of theoretical physics into ever more exotic realms of space-time and geometry. Cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid and dramatic that it defies ordinary comprehension. This epoch, known as cosmic inflation, stretched space itself at a rate that dwarfs any expansion we observe today. During inflation, regions of space smaller than a proton grew to encompass volumes larger than basketballs in less time than it takes light to cross an atomic nucleus. The theory of cosmic inflation emerged from attempts to solve several puzzling problems with the standard Big Bang cosmology. These problems seem to require remarkably precise initial conditions for the universe to evolve into the cosmos we observe today. Without inflation, the Big Bang model struggled to explain why the universe appears so uniform on large scales while simultaneously containing the small variations that seeded the formation of galaxies and stars. The horizon problem represents one of the most striking puzzles that inflation addresses. When we observe the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it has nearly identical temperature in all directions across the sky. This uniformity extends to regions that should never have been in causal contact, according to standard Big Bang cosmology. Consider two patches of sky separated by more than 2 degrees. In the standard model without inflation, these regions were so far apart in the early universe that light signals could not have traveled between them by the time the cosmic microwave background was emitted. Without any mechanism for communication or energy exchange, there's no apparent reason why these causally disconnected regions should have identical temperatures. Inflation solves this problem by proposing that all the regions we can observe today were once compressed into a tiny, causally connected volume before inflation began. During the inflationary epoch, this small region expanded exponentially, stretching causally connected patches to scales much larger than the observable universe. The uniform temperature we observe reflects the thermal equilibrium that existed in this primordial patch before inflation stretched it beyond recognition. The flatness problem poses another challenge for standard cosmology. Observations indicate that the geometry of space is remarkably close to perfectly flat, meaning that parallel lines never converge or diverge as they would in curved geometries. This flatness requires the density of matter and energy in the universe to be incredibly close to a critical value that separates eternal expansion from eventual recollapse. The problem is that this critical density represents an unstable equilibrium point. If the early universe had even slightly more than critical density, it would have quickly collapsed back on itself. If it had slightly less, it would have expanded so rapidly that matter could never clump together to form stars and galaxies. The observed near critical density seems to require fine-tuning the initial conditions to extraordinary precision. Inflation addresses the flatness problem through the exponential stretching of space during the inflationary epoch. Just as the surface of a balloon appears increasingly flat as you inflate it to larger sizes, the exponential expansion of inflation flattens any initial curvature in spacetime. Regions that began with significant curvature become geometrically flat through the enormous expansion factor of inflation. The monopole problem arises in grand unified theories that predict the existence of exotic particles called magnetic monopoles. These theoretical particles would be extremely massive and stable, and they should have been produced in large quantities during the high-energy conditions of the early Big Bang. The problem is that monopoles have never been observed, despite theoretical predictions that they should be common throughout the universe. Inflation dilutes the density of monopoles and other exotic relics through exponential expansion. Even if monopoles were produced in large numbers before inflation, the subsequent expansion would spread them so thinly throughout space that we would be unlikely to encounter any in the observable universe. This explains their apparent absence without requiring modifications to the underlying particle physics theories. The inflationary mechanism requires a scalar field called the inflaton that drives the exponential expansion through its potential energy. Unlike ordinary matter and radiation, which become diluted as space expands, the energy density of the inflaton field remains approximately constant during inflation. This constant energy density acts like Einstein's cosmological constant, driving accelerated expansion through its negative pressure. The inflaton field must satisfy specific conditions to produce successful inflation. Its potential energy function must be relatively flat over a large range of field values, allowing the field to change slowly while maintaining nearly constant energy density. This slow roll condition ensures that inflation lasts long enough to solve the horizon and flatness problems while remaining consistent with observations. Different models of inflation propose various forms for the inflaton potential. Chaotic inflation models involve large field excursions with polynomial potentials, while small field models work with more modest field values and carefully tuned potentials. Each model makes specific predictions for observational signatures that can potentially distinguish between different inflationary scenarios. The end of inflation occurs when the inflaton field reaches the minimum of its potential and begins oscillating around this minimum value. These oscillations decay through interactions with other fields, transferring the inflaton's energy into ordinary particles and radiation. This process, known as reheating, marks the transition from the inflationary epoch to the radiation-dominated era described by standard Big Bang cosmology. Quantum fluctuations during inflation provide the seeds for all large-scale structure in the universe. The inflaton field experiences quantum mechanical fluctuations that get stretched to cosmic scales by the exponential expansion. These quantum fluctuations become classical density variations after inflation ends, providing the gravitational seeds that eventually grow into galaxies, galaxy clusters, and the cosmic web. The scale invariant spectrum of these primordial fluctuations represents one of inflation's most successful predictions. Scale invariance means that fluctuations have similar amplitudes across a wide range of scales, creating the nearly flat spectrum observed in the cosmic microwave background. This prediction was made decades before precision measurements confirmed the scale invariant nature of primordial fluctuations. Gravitational waves produced during inflation offer another potential observational signature. Just as density fluctuations arise from quantum fluctuations in the inflaton field, tensor perturbations in space-time itself create a background of primordial gravitational waves. These gravitational waves would leave distinct polarization patterns in the cosmic microwave background that could potentially be detected by sensitive instruments. The search for B-mode polarization in the cosmic microwave background represents one of the most active areas in observational cosmology. B-modes would provide smoking gun evidence for gravitational waves from inflation and could constrain the energy scale at which inflation occurred. Several ground-based and space-based experiments are pushing toward the sensitivity needed to detect or rule out inflationary B-modes. Eternal inflation represents an extension of the basic inflationary scenario that has profound implications for our understanding of the universe's ultimate structure. In many inflationary models, inflation never completely ends, but continues in some regions while ending in others. This creates a fractal structure where inflating regions spawn pocket universes like ours through local terminations of inflation. The multiverse implications of eternal inflation suggest that our observable universe represents just one bubble in an infinite foam of causally disconnected domains. Each bubble universe might have different physical laws, constants, and dimensions determined by the specific way inflation ended in that region. This cosmic landscape provides a potential explanation for the apparent fine-tuning of physical constants that allow for the existence of complexity and life. String theory provides theoretical frameworks for realizing inflationary models within fundamental physics. String inflation models typically involve D-branes or other stringy objects whose dynamics can drive inflationary expansion. These models often predict specific relationships between observable parameters and fundamental physics, potentially offering windows into string theory through cosmological observations. Loop quantum cosmology offers alternative approaches to early universe physics that might modify or replace standard inflation. In these models, quantum gravitational effects bounce the universe from a previous contracting phase, potentially solving the horizon and flatness problems without requiring exponential expansion. These scenarios make different predictions for primordial fluctuations and gravitational wave backgrounds. Observational tests of inflation continue to improve with advancing technology and analysis techniques. Precision measurements of the cosmic microwave background by satellites like Planck have confirmed many inflationary predictions while constraining model parameters. future observations of gravitational waves, both primordial and astrophysical, may provide additional tests of inflationary physics. The problem of initial conditions for inflation remains a topic of active research. While inflation solves many fine-tuning problems of standard cosmology, it introduces new questions about what conditions are needed to start inflation in the first place. Some models require specific initial field configurations, while others claim to begin inflating from generic initial conditions. Inflation's relationship to fundamental physics continues to evolve as our understanding of quantum gravity, string theory, and particle physics advances. The inflationary paradigm has become deeply embedded in modern cosmology, but ongoing theoretical and observational work continues to refine our understanding of how inflation works and what it implies for the nature of space, time, and physical law. The measure problem in eternal inflation addresses questions about probability and prediction in an infinite multiverse. If eternal inflation produces infinitely many bubble universes with all possible properties, how can we calculate the probability of observing any particular set of physical laws or constants? Various proposals for defining measures on the space of possible universes remain controversial and unresolved. Alternative theories to inflation, such as ekpyrotic and cyclic cosmologies, propose different mechanisms for solving the standard cosmological problems. These models typically involve contracting phases or collisions between higher dimensional objects that create the conditions we observe. While less developed than inflationary theory, these alternatives provide important checks on the uniqueness of inflationary explanations. The connection between inflation and dark energy represents another frontier in cosmological research. Both phenomena involve accelerated expansion driven by fields with negative pressure, leading some physicists to explore whether they might be related aspects of a single underlying mechanism. Current acceleration might represent a new phase of inflation or an entirely different phenomenon. Inflation theory demonstrates how quantum mechanics and general relativity combine to shape the large-scale structure of the universe. The quantum fluctuations that arose during inflation, amplified by gravitational dynamics, created the seeds for every galaxy and star. This remarkable connection between microscopic quantum processes and cosmic architecture illustrates the deep unity underlying apparently disparate physical phenomena. The inflationary paradigm has fundamentally changed our conception of the Big Bang from a singular event to the ending of an earlier inflationary epoch. Rather than representing the absolute beginning of time and space, the Big Bang becomes a phase transition from exponential expansion to the more sedate expansion we observe today. This perspective opens new questions about what might have preceded inflation and whether time itself has a beginning. Understanding cosmic inflation requires grappling with exponential numbers and timescales far removed from everyday experience. The mathematical elegance of exponential expansion, where small changes in duration produce enormous changes in scale, reflects deep principles about how fields and spacetime interact under extreme conditions. These insights continue to guide theoretical physics toward ever more fundamental understanding of space, time, and the quantum vacuum that underlies all physical phenomena. Holographic principle. The holographic principle suggests that our three-dimensional reality might be an illusion, a projection from information encoded on a two-dimensional surface. This radical idea emerged from the study of black holes and has since transformed our understanding of space, time, gravity, and the fundamental nature of information itself. The principle proposes that everything we perceive as solid matter existing in three dimensions of space might actually be encoded on a distant boundary, much like how a hologram stores three-dimensional images on flat surfaces. The roots of this extraordinary concept trace back to Jacob Bekenstein's work on black hole thermodynamics in the 1970s. Bekenstein realized that black holes must possess entropy, a measure of their information content, because they have temperature and can absorb matter irreversibly. But when he calculated this entropy, he discovered something unexpected. It was proportional to the surface area of the black hole's event horizon, not its volume. This area-entropy relationship seemed counterintuitive. In ordinary systems, entropy typically scales with volume because it measures the number of microscopic states available to particles throughout a three-dimensional space. A gas in a larger container has more entropy because its molecules can occupy more positions. But black holes appear to violate this expectation, with their information content determined by their two-dimensional boundary rather than their three-dimensional interior. Stephen Hawking's discovery that black holes emit thermal radiation deepened this mystery. If black holes have temperature and entropy, they must be thermodynamic objects that can exchange energy and information with their surroundings. But this raised the troubling question of what happens to information that falls into a black hole when the black hole eventually evaporates through Hawking radiation. The information paradox emerged from the apparent conflict between quantum mechanics, which demands information conservation, and black hole physics, which seem to allow information destruction. Gerard 't Hooft and Leonard Susskind recognized that the area-entropy relationship might hold a deeper truth about the nature of space and information. They proposed that all the information contained within any volume of space could be encoded on that volume's boundary surface. This holographic principle suggests that three-dimensional physics is redundant, with all essential information stored on two-dimensional surfaces. The principle draws its name from optical holography, where three-dimensional images are reconstructed from interference patterns stored on two-dimensional photographic plates. When illuminated with coherent light, these flat holograms project realistic, three-dimensional scenes with proper depth and parallax. The holographic principle proposes that nature operates similarly, with our three-dimensional universe emerging from information encoded on its two-dimensional boundary. This boundary for our observable universe would exist at the cosmic horizon, the edge of the region from which light can reach us. All the complexity we observe in galaxies, stars, planets, and life itself might be projections from information patterns encoded on this distant surface. The principle doesn't deny the reality of our experience, but suggests that this reality has a more fundamental description in terms of boundary information. The ADS-CFT correspondence provides the most concrete realization of holographic duality. This correspondence relates string theory in negatively curved spacetime called anti-de Sitter space to conformal field theory living on the boundary of that space. The interior gravity theory and the boundary field theory contain exactly the same information, offering different but equivalent descriptions of the same physics. In ADS-CFT, gravitational phenomena in the bulk spacetime correspond to quantum field theory processes on the boundary. Black holes in the interior correspond to thermal states in the boundary theory. Gravitational collapse and formation correspond to thermalization processes. Even the emergence of space and time in the bulk can be understood as arising from entanglement patterns in the boundary theory. This correspondence demonstrates that gravity itself might be an emergent phenomenon rather than a fundamental force. The attractive force that keeps our feet on the ground and governs planetary motion might arise from quantum mechanical processes occurring on a distant boundary. Space and time, rather than being the fundamental arena in which physics takes place, could be derived concepts that emerge from more basic information processing on holographic surfaces. The holographic principle offers new perspectives on the black hole information paradox. If all information that falls into a black hole is encoded on its event horizon rather than lost in the interior, then this information remains accessible in principle even as the black hole interior becomes causally disconnected from the outside universe. As the black hole evaporates through Hawking radiation, the horizon-encoded information could gradually be released back to the external universe. However, this resolution faces challenges. The information stored on the horizon would be scrambled in extremely complex ways, making it practically impossible to decode, even if it's theoretically preserved. The process of extracting information from black hole radiation might require quantum operations so complex that they exceed any realistic computational capabilities. Quantum error correction provides tools for understanding how information might be preserved and protected in holographic systems. Just as quantum computers use error correction to maintain coherent information despite noise and decoherence, holographic systems might implement natural error correction mechanisms that preserve information even when local regions are damaged or lost. The principle has profound implications for our understanding of space and locality. If physics can be completely described by boundary information, then the notion of local interactions in the bulk becomes questionable. Events that appear to occur at specific locations in three-dimensional space might actually reflect global properties of the boundary information. This challenges our intuitive understanding of cause and effect in local regions of space-time. Entanglement plays a crucial role in holographic theories, serving as the mechanism that weaves space and time from quantum information. Regions of space that are connected correspond to entangled regions of the boundary theory. The geometry of space-time emerges from the pattern of quantum entanglement in the holographic description. This entanglement geometry correspondence suggests that space itself is not fundamental, but emerges from quantum information processing. Distance between points in space reflects the strength of entanglement between corresponding boundary regions. More entanglement creates shorter distances, while less entanglement corresponds to greater spatial separation. The holographic principle extends beyond black holes to cosmology and the structure of our universe. If our universe is holographic, then all the information describing cosmic evolution, structure formation, and the emergence of life might be encoded on the cosmic microwave background or other boundary surfaces. The three-dimensional history of our universe could be a projection from two-dimensional information processing. Cosmological holography faces challenges in understanding what surface serves as the holographic boundary for our expanding universe. Unlike black holes, which have well-defined event horizons, cosmological boundaries are more subtle and depend on the specific model of space-time geometry. Different proposals suggest various surfaces, from particle horizons to future event horizons to more exotic geometric constructions. The principle also connects to theories of quantum gravity and attempts to understand how space-time emerges from more fundamental quantum mechanical processes. Loop quantum gravity, causal set theory, and other approaches all grapple with similar questions about how classical space-time arises from discrete quantum building blocks. Experimental tests of holographic ideas remain challenging because the holographic boundaries typically lie far from direct experimental access. However, condensed matter systems provide laboratories for studying holographic physics. Certain materials exhibit behavior that can be understood through holographic duality, offering insights into how holographic principles might operate in accessible physical systems. The principle has inspired new approaches to understanding complexity, information theory, and the emergence of classical physics from quantum foundations. Holographic complexity measures how difficult it would be to construct particular quantum states from simple initial conditions. These measures provide new tools for understanding how complexity evolves in quantum systems and how classical physics emerges from quantum foundations. Machine learning and artificial intelligence research has found inspiration in holographic ideas, particularly in understanding how complex behaviors can emerge from simpler underlying patterns. The principle of dimensional reduction, where high-dimensional data can be understood through lower-dimensional representations, echoes themes from holographic physics. The philosophical implications of the holographic principle are staggering. If our three-dimensional reality is indeed a projection from two-dimensional information, it challenges basic assumptions about the nature of existence, substance, and experience. The solid objects around us, the space we move through, and even our own bodies might be emergent patterns in a more fundamental information processing substrate. This doesn't necessarily make our experience less real or meaningful. A holographic projection can contain all the same information and structure as a three-dimensional object. The principle might simply reveal that reality has more layers and subtlety than our everyday experience suggests. Our three-dimensional perspective might be the natural way to understand and interact with holographically encoded information. The principle also raises questions about consciousness and observation. If the physical world emerges from boundary information processing, where does consciousness fit into this picture? Some speculative theories suggest that consciousness itself might involve holographic information processing, with subjective experience emerging from patterns of information integration across multiple scales. Current research continues to develop and test holographic ideas across various domains of physics. String theorists work to understand how holographic duality extends beyond the AD-S-CFT correspondence to more realistic spacetimes. Condensed matter physicists explore holographic descriptions of quantum phase transitions and strongly correlated systems. Cosmologists investigate holographic approaches to understanding dark energy, inflation, and the multiverse. The holographic principle represents one of the most radical ideas in modern theoretical physics, suggesting that our most basic intuitions about space, dimension, and locality might be incomplete or misleading. Whether or not the principle applies to our actual universe remains an open question, but its exploration has already yielded profound insights into the nature of gravity, information, and quantum mechanics. The principle demonstrates how physics continues to reveal reality as stranger and more subtle than everyday experience suggests. Like quantum mechanics before it, holographic physics challenges us to expand our conceptual frameworks and consider possibilities that initially seem impossible or absurd. The holographic universe, if real, would represent the ultimate example of how appearances can deceive and how mathematical physics can reveal hidden depths in the nature of existence itself. The Higgs mechanism. The Higgs mechanism represents one of the most profound insights in particle physics, explaining how the fundamental particles that make up matter acquire their masses. This elegant theoretical framework resolves a deep puzzle about the nature of mass itself, while preserving the mathematical symmetries that physicists believe must underlie the laws of nature. The mechanism involves a field that permeates all of space, interacting with particles in ways that give them their characteristic masses while leaving others completely massless. The story begins with a fundamental problem in particle physics. The forces that govern atomic nuclei and radioactive decay operate through particles called W and Z bosons. These force-carrying particles are extremely massive, about 80 to 90 times heavier than protons. This enormous mass creates difficulties for the mathematical theories that describe these forces, because massive gauge bosons violate the elegant symmetries that physicists use to construct consistent quantum field theories. Gauge symmetries represent the mathematical foundation of our understanding of fundamental forces. These symmetries allow physicists to change the mathematical description of fields at every point in space without altering any physical predictions. Electromagnetism, the weak nuclear force, and the strong nuclear force all arise from different types of gauge symmetries that constrain how particles can interact with each other. The problem is that giving mass to gauge bosons explicitly breaks these crucial symmetries. When physicists tried to write down theories with massive W and Z bosons, they encountered mathematical inconsistencies and infinite results that couldn't be removed through standard techniques. The theories lost their predictive power and seemed fundamentally flawed, yet experimental evidence clearly showed that W and Z bosons do indeed possess large masses. The resolution came through understanding how symmetries can be spontaneously broken without being explicitly violated in the underlying laws of physics. Spontaneous symmetry breaking occurs when the ground state of a system has less symmetry than the laws governing the system. The laws remain perfectly symmetric, but the state the system actually occupies breaks that symmetry. Consider a pencil balanced perfectly on its tip. The laws of gravity treat all horizontal directions equally, exhibiting perfect rotational symmetry. But the pencil cannot actually remain balanced in this symmetric configuration. It must fall in some particular direction, spontaneously breaking the rotational symmetry even though gravity itself remains perfectly symmetric. Peter Higgs, along with Robert Brout, François Englert, Gerald Guralnick, Carl Hagen, and Tom Kibble, realized that a similar mechanism could give mass to gauge bosons without explicitly breaking gauge symmetry. They proposed the existence of a scalar field, now called the Higgs field, that fills all of space and has a non-zero value in its lowest energy state. The Higgs field differs fundamentally from other quantum fields in that its vacuum expectation value is not zero. Most fields have no value in empty space, activated only when particles or excitations are present. But the Higgs field maintains a constant, non-zero value throughout the universe, even in regions containing no matter or other fields. This omnipresent field creates the backdrop against which all other physics unfolds. The shape of the Higgs potential energy determines how spontaneous symmetry breaking occurs. Rather than having its minimum at zero field value, the Higgs potential has its minimum at some non-zero value. The field naturally settles into this minimum energy configuration, establishing a non-zero vacuum expectation value that breaks the underlying gauge symmetry. This symmetry breaking gives mass to the W and Z bosons through their interaction with the Higgs field's vacuum expectation value. The strength of each boson's interaction with the Higgs field determines its mass. The photon, which doesn't interact with the Higgs field, remains massless and continues to mediate the electromagnetic force with infinite range. The mechanism preserves gauge invariance by making the symmetry breaking spontaneous rather than explicit. The underlying equations remain perfectly symmetric, but the vacuum state around which physics is organized breaks this symmetry. This allows physicists to maintain the mathematical consistency of gauge theories while explaining the observed masses of fundamental particles. Fermions, the matter particles like electrons and quarks, acquire mass through a different but related mechanism. They couple directly to the Higgs field through interactions called Yukawa couplings. The strength of each fermion's Yukawa coupling determines its mass, with stronger couplings producing heavier particles. Neutrinos have extremely small masses because their couplings to the Higgs field are extraordinarily weak. The Higgs boson emerges as a quantum excitation of the Higgs field, much like photons are excitations of the electromagnetic field. When the Higgs field fluctuates around its vacuum expectation value, these fluctuations manifest as Higgs particles that can be created and detected in high-energy experiments. The Higgs boson's properties are determined by the same potential that drives spontaneous symmetry breaking. Discovering the Higgs boson required building the most powerful particle accelerator ever constructed. The Large Hadron Collider at CERN accelerates protons to nearly the speed of light and collides them with enormous energies. These collisions occasionally produce Higgs bosons, which immediately decay into other particles that can be detected and analyzed. The discovery announcement in July 2012 marked the culmination of decades of theoretical development and experimental effort. Two independent experiments, ATLAS and CMS, both observed clear evidence for a new particle with properties consistent with the predicted Higgs boson. This discovery completed the standard model of particle physics and confirmed the mechanism that gives mass to fundamental particles. The Higgs mechanism extends beyond explaining particle masses to address deeper questions about the nature of empty space itself. The non-zero vacuum expectation value of the Higgs field means that what we perceive as empty space actually contains a uniform background of Higgs field energy. This gives the vacuum itself a complex structure with profound implications for cosmology and quantum field theory. Phase transitions in the early universe played crucial roles in establishing the current pattern of symmetry breaking. At extremely high temperatures, shortly after the Big Bang, thermal energy prevented the Higgs field from settling into its symmetry-breaking vacuum state. As the universe cooled, the Higgs field underwent a phase transition, spontaneously breaking electroweak symmetry and giving masses to the W and Z bosons. This electroweak phase transition separated the electromagnetic and weak nuclear forces, which at high energies appear as different aspects of a single unified electroweak force. The cooling universe naturally evolved from a symmetric high-energy state to the broken symmetry low-energy state we observe today, with distinct electromagnetic and weak forces mediated by massless photons and massive W and Z bosons respectively. The hierarchy problem represents one of the major puzzles that the Higgs mechanism raises but doesn't fully resolve. The Higgs boson mass receives quantum corrections from interactions with other particles, and these corrections should be enormous unless the parameters of the theory are fine-tuned to incredible precision. This suggests either remarkable coincidence or new physics beyond the standard model that naturally explains the hierarchy of mass scales. Supersymmetry offers one potential solution to the hierarchy problem by introducing partner particles that cancel the large quantum corrections to the Higgs mass. In supersymmetric theories, every known particle has a superpartner with opposite spin statistics, and the quantum contributions from particles and superpartners cancel each other to produce naturally light Higgs bosons. Alternative approaches to electroweak symmetry breaking propose that the Higgs mechanism might be replaced by entirely different dynamics. Technicolor theories suggest that new, strong interactions could break electroweak symmetry without requiring fundamental scalar fields. Composite Higgs models propose that the Higgs boson itself might be made of more fundamental constituents, similar to how protons are made of quarks. The discovery of the Higgs boson opened new experimental frontiers for testing the standard model and searching for physics beyond it. Precise measurements of the Higgs boson's properties can reveal whether it behaves exactly as predicted or shows deviations that indicate new physics. The coupling strengths to different particles, the boson's self-interactions and its quantum numbers all provide windows into fundamental physics. Multiple Higgs doublet models extend the standard model by including additional Higgs fields with different vacuum expectation values and particle interactions. These models can address questions like why there are 3 generations of fermions and whether CP violation in the Higgs sector might explain the matter-antimatter asymmetry of the universe. The Higgs mechanism also connects to cosmological puzzles like dark matter and dark energy. Some models propose that the dark matter consists of particles that interact primarily through the Higgs sector, while others suggest connections between the Higgs field and the mysterious dark energy that drives cosmic acceleration. Vacuum stability represents another frontier where Higgs physics intersects cosmology. The current vacuum state might not be the absolute minimum of the Higgs potential, but rather a metastable state that could eventually decay to a lower energy configuration. Such a transition would have catastrophic consequences for the structure of matter and the laws of physics as we know them. Quantum field theory calculations suggest that the standard model vacuum might indeed be metastable, with a lifetime much longer than the current age of the universe, but not infinite. Understanding the precise shape of the Higgs potential and the stability of our current vacuum requires both theoretical advances and more precise experimental measurements of Higgs properties. The Higgs mechanism demonstrates how mathematical symmetry and physical reality interact in subtle ways. The mechanism preserves the mathematical elegance that physicists believe must underlie natural laws while explaining the asymmetric world we actually observe. This interplay between hidden symmetries and manifest asymmetries reflects deep principles about how complex structures emerge from simple underlying rules. Modern research continues to probe the implications of the Higgs mechanism for fundamental physics. Scientists investigate whether the mechanism extends to give mass to neutrinos, whether additional Higgs-like fields exist, and how the mechanism might connect to theories of quantum gravity. Each new measurement and theoretical insight adds to our understanding of this elegant solution to one of particle physics' most fundamental puzzles. The Higgs mechanism stands as a testament to the power of theoretical physics to predict and explain phenomena at the deepest levels of reality. From its origins in abstract mathematical symmetries to its experimental confirmation in the world's most sophisticated scientific instruments, the mechanism illustrates how human reason and ingenuity can penetrate the fundamental mysteries of mass, energy, and the structure of physical law itself. CP violation. Deep within the quantum realm lies a subtle asymmetry that may explain one of the most fundamental questions about our existence. Why does the universe contain matter instead of equal amounts of matter and antimatter? This asymmetry, known as CP violation, represents a tiny but crucial deviation from the perfect symmetries that physicists once believed governed all natural processes. The discovery and understanding of CP violation has revolutionized our comprehension of particle physics and cosmology, revealing that nature exhibits a slight preference for matter over antimatter. To understand CP violation, we must first examine the symmetries that physicists expected nature to respect. Charge conjugation, or C-symmetry, transforms every particle into its antiparticle. Under this symmetry, electrons become positrons, protons become antiprotons, and so forth. If C-symmetry held perfectly, the universe would look identical whether we replaced every particle with its antiparticle. Parity, or P-symmetry, reflects the spatial coordinates, essentially creating a mirror image of any physical system. Under P-symmetry, left becomes right, and clockwise becomes counterclockwise. For decades, physicists assumed that the laws of physics were identical in our world and its mirror image, making no fundamental distinction between left and right. The combination of these symmetries, called CP symmetry, transforms particles into antiparticles while simultaneously creating a mirror image of space. Under CP transformation, a left-handed electron becomes a right-handed positron, and a clockwise spinning proton becomes a counter-clockwise spinning antiproton. The assumption that nature respects CP symmetry seemed so fundamental that it became deeply embedded in theoretical physics. The first crack in this symmetrical worldview appeared in 1956, when Tsung-Dao Lee and Chen-Ning Yang suggested that parity might not be conserved in weak nuclear interactions. Their proposal seemed so radical that many physicists initially dismissed it, but Chien-Shiung Wu's elegant experiment with cobalt-60 nuclei proved them correct. The weak force responsible for certain types of radioactive decay indeed violates parity symmetry. Wu's experiment involved cooling cobalt-60 nuclei to extremely low temperatures and aligning their spins using powerful magnetic fields. If parity were conserved, the radioactive decay products should emerge equally in all directions. Instead, Wu observed that electrons from the decay were preferentially emitted in the direction opposite to the nuclear spin, demonstrating clear parity violation in weak interactions. This discovery shocked the physics community but initially seemed containable within a modified theoretical framework. Even if parity was violated, physicists hoped that the combined CP symmetry might still be preserved. Under this assumption, while left and right might be distinguishable, the combined operation of changing particles to antiparticles and reversing spatial coordinates would still leave physics unchanged. The assumption of CP conservation implied that matter and antimatter should behave in perfectly symmetric ways. Any process that occurred in the matter world should have an exact antimatter counterpart, ensuring that the universe could contain equal amounts of both. This symmetry seemed essential for understanding the fundamental balance between matter and antimatter in cosmology. However, in 1964, James Cronin and Val Fitch discovered that even CP symmetry is not perfectly conserved. Their experiments studied the decay of neutral kaons, particles that exist in quantum superpositions of matter and antimatter states. According to CP conservation, certain decay modes should be absolutely forbidden, but Cronin and Fitch observed these forbidden decays occurring at a tiny but measurable rate. Neutral kaons provide an ideal laboratory for studying CP violation because they can oscillate between particle and antiparticle states. The K0 meson and its antiparticle, the K0 bar meson, can transform into each other through weak interactions. This oscillation creates mixed states that are superpositions of matter and antimatter, making subtle asymmetries detectable through precision measurements. The CP-violating decays observed by Cronin and Fitch occurred in only about 2 parts in 1,000, representing an extremely small deviation from perfect symmetry. This tiny asymmetry was so subtle that it had escaped detection in all previous experiments, yet its implications were profound. The discovery showed that nature exhibits a fundamental preference for matter over antimatter, breaking one of the most basic symmetries that physicists had assumed must govern natural processes. The theoretical understanding of CP violation advanced significantly with the development of the Standard Model of Particle Physics. Makoto Kobayashi and Toshihide Masukawa proposed that CP violation could arise naturally from the complex phases in the mixing matrix that describes how different types of quarks transform into one another through weak interactions. The Kobayashi-Masukawa mechanism requires at least 3 generations of quarks to produce observable CP violation. With only 2 generations, the mixing matrix can always be made real through appropriate phase choices, eliminating any source of CP violation. But with 3 generations, irreducible complex phases appear that cannot be removed, providing the theoretical foundation for CP violating phenomena. This mechanism connects CP violation to the fundamental structure of particle physics, linking the observed matter-antimatter asymmetry to the existence of multiple generations of fermions. The discovery of the charm, bottom, and top quarks confirmed the 3-generation structure predicted by the Kobayashi-Masukawa theory, providing crucial support for this understanding of CP violation. Experimental studies of CP violation expanded beyond kaon systems to include B-mesons, particles containing bottom quarks. B-meson experiments at facilities like Baubar and Bell have measured CP violation in numerous decay channels, confirming the Kobayashi-Masukawa mechanism with high precision. These measurements have mapped out the structure of CP violation in the quark sector and tested the consistency of the Standard Model. The observation of CP violation in B-mesons revealed that the asymmetry is more pronounced in some decay channels than others. Certain decays show CP violation effects of several percent, much larger than the tiny asymmetries first observed in kaon decays. This variation demonstrates that CP violation is not a uniform property, but depends on the specific particles and interactions involved. Recent discoveries have extended CP violation beyond the quark sector. The T2K neutrino experiment has found evidence for CP violation in neutrino oscillations, suggesting that neutrinos and antineutrinos might behave differently as they change from one type to another. This observation opens new frontiers in understanding how CP violation manifests across different sectors of particle physics. The connection between CP violation and cosmology represents one of the most profound implications of this phenomenon. In the early universe, if matter and antimatter had been created in exactly equal quantities, they would have annihilated completely, leaving behind only photons and no material structures. The existence of galaxies, stars, planets, and life itself requires an initial asymmetry favoring matter over antimatter. Andrei Sakharov identified 3 conditions necessary for generating this cosmic matter-antimatter asymmetry: baryon number violation, C and CP violation, and departure from thermal equilibrium. CP violation provides one of these essential ingredients, but the amount of CP violation observed in the Standard Model appears insufficient to explain the observed cosmic asymmetry by many orders of magnitude. This quantitative shortfall suggests that additional sources of CP violation, beyond those in the Standard Model, must have operated in the early universe. Grand unified theories, supersymmetric models, and other extensions of the Standard Model propose mechanisms that could amplify CP violation to cosmologically relevant levels. These theories predict new particles and interactions that could leave observable signatures in current experiments. The search for new sources of CP violation has motivated precision measurements of electric dipole moments in atoms, molecules, and fundamental particles. A permanent electric dipole moment in a symmetric particle would indicate CP violation through the coupling of the particle's spin to an external electric field. Current experiments probe electric dipole moments with extraordinary sensitivity, searching for deviations from Standard Model predictions. CP violation also plays crucial roles in understanding the evolution of the early universe during phase transitions and symmetry-breaking events. As the universe cooled and underwent various phase transitions, CP-violating processes could have influenced the relative abundances of matter and antimatter, potentially amplifying small initial asymmetries into the large matter dominance we observe today. The study of CP violation has advanced experimental techniques and theoretical methods throughout particle physics. The precision required to detect tiny asymmetries has driven innovations in detector technology, data analysis, and statistical methods. These advances have found applications throughout physics, from fundamental particle research to practical applications in medical imaging and materials science. Theoretical understanding of CP violation has also advanced our comprehension of quantum field theory, symmetry breaking, and the structure of physical laws. The realization that fundamental symmetries can be subtly broken has influenced thinking about spontaneous symmetry breaking, gauge theories, and the emergence of physical phenomena from underlying mathematical structures. Future experiments continue to probe CP violation with ever-increasing precision. The Large Hadron Collider Beauty experiment studies CP violation in B-Meson systems with unprecedented statistical power, while next-generation neutrino experiments aim to measure CP violation in the neutrino sector with high precision. These measurements will test our understanding of CP violation and search for deviations that might point toward new physics. The philosophical implications of CP violation challenge our understanding of symmetry and natural law. The discovery that nature exhibits subtle preferences challenges assumptions about the fundamental balance and symmetry that many expected to characterize physical law. This asymmetry reminds us that nature is under no obligation to conform to our aesthetic expectations about mathematical beauty and symmetrical principles. CP violation demonstrates how tiny effects can have enormous consequences. The minute asymmetries observed in particle decay experiments connect directly to the grandest questions about cosmic evolution and the existence of material structures in the universe. This connection illustrates how fundamental physics research, even when focused on seemingly esoteric phenomena, can illuminate the deepest mysteries of existence. The ongoing study of CP violation continues to reveal new aspects of this fundamental asymmetry. As experimental techniques improve and theoretical understanding advances, physicists uncover additional manifestations of CP violation and explore its connections to other areas of physics. Each new discovery adds to our understanding of why the universe exhibits the subtle but crucial preference for matter that makes our existence possible. Understanding CP violation requires grappling with the interplay between symmetry and asymmetry in fundamental physics. While perfect symmetries provide elegant mathematical frameworks for understanding natural laws, the observed universe clearly exhibits crucial asymmetries that shape its structure and evolution. CP violation represents one of the most important examples of how reality transcends our symmetrical expectations, revealing a universe that is both mathematically beautiful and subtly biased toward the emergence of complexity and structure. Entropy and arrow of time. Time flows in only one direction, carrying the universe from past to future in an irreversible march toward greater disorder. This temporal asymmetry, known as the arrow of time, emerges from the statistical behavior of countless microscopic particles and the fundamental principle that isolated systems tend toward states of maximum entropy. Understanding why time has a direction requires exploring the deep connections between thermodynamics, statistical mechanics, and the large-scale structure of the cosmos itself. The concept of entropy began with attempts to understand the efficiency of steam engines in the 19th century. Engineers noticed that heat engines could never convert thermal energy into work with perfect efficiency, always wasting some energy as heat that flows to cooler reservoirs. This observation led Rudolf Clausius to formulate the second law of thermodynamics. The entropy of an isolated system can only increase or remain constant, never decrease spontaneously. Entropy measures the degree of disorder or randomness in a system, but this informal definition obscures its deeper statistical foundation. Ludwig Boltzmann revealed that entropy fundamentally counts the number of microscopic arrangements that correspond to the same macroscopic state. A gas uniformly distributed throughout a container has high entropy because there are many ways to arrange the molecules while maintaining uniform density and temperature. Consider a simple example: a box divided by a partition with gas molecules initially confined to one half. When the partition is removed, the molecules spread throughout the entire box, increasing the system's entropy. This expansion occurs because there are vastly more ways to arrange molecules throughout the full volume than to keep them confined to one half. The molecules don't actively seek disorder, rather, they naturally explore all available configurations, and disordered states vastly outnumber ordered ones. The statistical nature of entropy explains why it almost always increases in isolated systems. While individual molecules follow perfectly reversible laws of motion, their collective behavior exhibits irreversible trends toward greater disorder. A drop of ink spreading through water demonstrates this principle. The molecular motions that mix the ink and water are individually reversible, but the statistical improbability of all molecules spontaneously unmixing makes the process effectively irreversible. This statistical irreversibility creates the thermodynamic arrow of time. Entropy provides a cosmic clock that distinguishes past from future. The past is the direction of lower entropy, while the future points toward higher entropy. Hot coffee cooling to room temperature, ice melting in warm air, and perfume dispersing through a room all exemplify processes that increase entropy and define the direction of temporal flow. But this raises a profound puzzle. If the fundamental laws of physics are time reversible, why does the universe exhibit such strong temporal asymmetry? Newton's laws, Maxwell's equations, and even Einstein's relativity treat past and future symmetrically. A movie of planetary motion played backward shows equally valid physics, yet a movie of an egg unscrambling itself appears absurd because it violates our experience of entropy increase. The resolution lies in recognizing that the second law of thermodynamics is not a fundamental dynamical law, but a statistical statement about initial conditions. The universe began in a state of extraordinarily low entropy, with matter and energy distributed in highly ordered configurations. The cosmic microwave background radiation shows that the early universe was remarkably smooth and uniform, representing a state of much lower entropy than the clumpy, structured universe we observe today. This special initial condition set up the entropy gradient that drives the arrow of time throughout cosmic history. As the universe evolves from its low entropy beginning toward higher entropy states, irreversible processes naturally emerge. The formation of stars and galaxies, the evolution of life, and the flow of heat from hot to cold objects all participate in the universe's overall march toward greater disorder. Gravitational systems exhibit peculiar entropy behavior that complicates this picture. Unlike gases, which maximize entropy by spreading uniformly through space, gravitational systems can decrease their entropy by clumping together. When gas clouds collapse to form stars, their gravitational potential energy converts to heat that radiates away, leaving behind more concentrated, apparently lower entropy, configurations. However, this local entropy decrease is more than compensated by the entropy increase of the radiated heat. The formation of stars and other gravitational structures actually accelerates the universe's overall entropy production by creating efficient engines for converting organized gravitational energy into random thermal radiation. Black holes represent the ultimate manifestation of this process, concentrating matter into regions of extreme entropy density. The thermodynamic arrow of time aligns with several other temporal asymmetries observed in nature. The electromagnetic arrow points from past to future because we observe retarded potentials rather than advanced ones. Charges create electromagnetic waves that propagate outward from their sources rather than converging inward from infinity. This asymmetry reflects boundary conditions in the distant past and future rather than fundamental time reversal violation. The cosmological arrow of time points in the direction of universal expansion. The universe grows larger and cooler as time progresses, creating a cosmic background against which all other temporal processes unfold. This expansion began with the Big Bang and continues today, driven by the initial conditions established during inflation and subsequent cosmic evolution. Quantum mechanics introduces additional temporal asymmetries through the measurement process. Quantum systems evolve reversibly according to the Schrödinger equation, but measurement appears to introduce irreversible wave function collapse that distinguishes past from future. Whether this represents fundamental time reversal violation or emerges from thermodynamic considerations in macroscopic measuring devices remains debated. The psychological arrow of time emerges from the thermodynamic arrow through the physics of memory formation and information processing. Brains store memories by creating correlations between present neural states and past events, a process that necessarily increases entropy. The subjective flow of time from past to future reflects the thermodynamic cost of maintaining and updating the information structures that constitute consciousness and memory. Biological evolution provides another example of how the arrow of time manifests in complex systems. While individual organisms age and die in accordance with thermodynamic principles, populations can evolve toward greater complexity and organization. This apparent contradiction resolves when we recognize that evolution operates as an open system driven by energy from the sun, allowing local decreases in entropy while contributing to the universe's overall entropy increase. The heat death of the universe represents the ultimate triumph of the second law of thermodynamics. In this far future scenario, all energy becomes uniformly distributed at the same temperature throughout space, eliminating any possibility of performing work or driving organized processes. Stars burn out, black holes evaporate, and the universe reaches maximum entropy in a state of thermal equilibrium. However, this heat death scenario assumes that our current understanding of physics remains valid over cosmic timescales. Quantum fluctuations, vacuum instability, and unknown physics might intervene before the universe reaches true thermodynamic equilibrium. The extremely long time scales involved, vastly exceeding the current age of the universe, make definitive predictions impossible. The arrow of time also connects to fundamental questions about the nature of physical law and the role of initial conditions in determining cosmic evolution. Some physicists argue that the special low-entropy initial state of the universe requires explanation, perhaps through inflationary cosmology or anthropic selection effects. Others contend that the arrow of time is simply a brute fact about our cosmic environment. Fluctuation theorems in modern statistical mechanics have refined our understanding of entropy production in small systems and finite time intervals. These theorems show that while entropy increases on average, significant fluctuations can occur in small systems or over short times, Such fluctuations don't violate the second law but demonstrate its statistical character and limits of applicability. Time reversal violation in particle physics provides another window into temporal asymmetry. CP violation in weak interactions means that certain particle processes occur at different rates when played backward in time. While these effects are tiny and don't directly influence macroscopic thermodynamics, they represent fundamental departures from time reversal symmetry in the laws of nature. The emergence of complexity and organization in the universe poses interesting challenges for understanding entropy and temporal asymmetry. While the second law demands overall entropy increase, it permits the formation of complex structures like life, civilization, and technology that represent local decreases in disorder. These islands of complexity exist within the broader context of entropy increase, powered by energy flows that ultimately trace back to the low-entropy initial conditions of the universe. Information theory has provided new perspectives on entropy and time asymmetry. The relationship between thermodynamic entropy and information entropy, established by Claude Shannon and others, reveals deep connections between physical processes and computation. The erasure of information necessarily generates heat and increases entropy, linking the processing of information to the arrow of time. Modern research continues to explore the foundations of temporal asymmetry and its relationship to fundamental physics. Studies of quantum thermodynamics investigate how quantum effects modify traditional thermodynamic concepts, while research into the emergence of space-time from quantum gravity might reveal new aspects of temporal asymmetry at the most fundamental level. The arrow of time remains one of the most profound and puzzling aspects of our physical reality. It connects the microscopic world of individual particles to the macroscopic phenomena of everyday experience, linking statistical mechanics to cosmology and consciousness. Understanding why time flows in one direction continues to challenge physicists and philosophers, revealing deep truths about the nature of existence itself. The statistical foundation of temporal asymmetry reminds us that the arrow of time emerges from the collective behavior of countless microscopic components, rather than from fundamental temporal asymmetry in physical law. This perspective suggests that time's direction is not built into the basic structure of reality, but emerges from the particular initial conditions and boundary conditions that characterize our cosmic environment. As our understanding of entropy and time asymmetry continues to evolve through advances in statistical mechanics, quantum field theory, and cosmology, we gain deeper appreciation for the subtle interplay between order and disorder that shapes the structure and evolution of the universe. The arrow of time stands as a testament to the power of statistical thinking and the profound connections between physics, information, and the nature of temporal experience itself. Maxwell's demon. In 1867, James Clerk Maxwell proposed a thought experiment that would challenge the fundamental understanding of thermodynamics for over a century. He imagined a tiny, intelligent being capable of observing and manipulating individual molecules, stationed at a doorway between two chambers filled with gas. This hypothetical creature, later dubbed Maxwell's demon, could seemingly violate the second law of thermodynamics by sorting fast and slow molecules to create temperature differences without expending energy. The demon operates by opening and closing a small door between two gas chambers. When a fast-moving molecule approaches from the left, the demon opens the door, allowing it to pass into the right chamber. When a slow molecule approaches from the left, the demon keeps the door closed. Conversely, slow molecules from the right are allowed to pass left, while fast ones are blocked. Through this selective sorting, the demon concentrates fast molecules in one chamber and slow molecules in the other. Since temperature correlates with average molecular speed, this sorting process creates a temperature difference between the chambers without any apparent work being performed. The right chamber becomes hot, while the left chamber becomes cold. This temperature difference could then drive a heat engine to perform useful work, seemingly extracting energy from thermal equilibrium and violating the second law of thermodynamics. The second law states that the entropy of an isolated system cannot decrease spontaneously. Entropy measures disorder, and the spontaneous separation of fast and slow molecules represents a decrease in disorder that should be impossible according to thermodynamic principles. If Maxwell's demon could operate successfully, it would enable the construction of perpetual motion machines that extract work from uniform temperature environments. The paradox troubled physicists because the demon's actions appeared to require no energy expenditure. The creature simply observes molecules and opens or closes a massless door accordingly. No force is exerted against molecular motion, no energy appears to be consumed, yet the result creates useful temperature differences that could power engines indefinitely. Early attempts to resolve the paradox focused on the physical requirements for the demon's operation. Some argued that the demon must exert forces to operate the door, consuming energy in the process. Others suggested that the demon's sensing apparatus would require energy to detect approaching molecules. However, these solutions seemed unsatisfactory because they could potentially be circumvented through clever engineering of the demon's mechanism. The breakthrough came from recognizing that information processing, not just physical manipulation, requires energy expenditure. Rolf Landauer demonstrated in 1961 that the erasure of information necessarily generates heat and increases entropy. This principle, known as Landauer's erasure principle, showed that computation and memory operations are fundamentally linked to thermodynamics. Landauer's insight revealed that Maxwell's demon must acquire, store, and eventually erase information about molecular positions and velocities. To operate the door selectively, the demon must remember which molecules are approaching and their speeds. This information must be stored in some form of memory, whether biological, mechanical, or electronic. The critical realization was that this memory cannot grow indefinitely. It must eventually be cleared to make room for new information. The process of erasing stored information irreversibly increases the entropy of the demon's environment. When a memory bit is reset from a definite state to a blank state, the information it contained is lost forever, and this loss manifests as heat dissipation. The amount of entropy generated by erasure exactly compensates for the entropy decrease achieved by molecular sorting, preserving the second law of thermodynamics. Charles Bennett further developed this resolution by showing that the demon could operate reversibly during the measurement and door operation phases. The entropy violation occurs specifically during the memory erasure step, which is unavoidable if the demon is to continue functioning indefinitely. Without periodic memory clearing, the demon's storage capacity would be exhausted, preventing further operation. This resolution connected Maxwell's demon to fundamental questions about the relationship between information and physics. It established that information is not an abstract concept separate from physical reality, but has concrete thermodynamic consequences. The mere act of forgetting information generates heat and increases entropy, making information processing subject to thermodynamic constraints. The demon paradox also illuminated the role of feedback control in thermodynamic systems. The demon represents an autonomous feedback controller that uses measurement information to influence system behavior. Real feedback systems, from biological organisms to electronic controllers, all face similar thermodynamic constraints when processing information about their environment. Modern reformulations of Maxwell's demon explore scenarios with quantum mechanical systems and sophisticated information processing protocols. Quantum versions of the demon must contend with additional complications, from measurement-induced decoherence and quantum uncertainty. The quantum demon cannot perfectly measure particle states without disturbing the system, introducing fundamental limits beyond those imposed by classical thermodynamics. Experimental realizations of demon-like systems have been constructed using micro and nanoscale devices. These experiments typically involve Brownian particles in carefully controlled environments, where external feedback can bias random thermal motion. While these systems cannot violate thermodynamics, they demonstrate how information can be used to extract work from thermal fluctuations, up to the fundamental limits imposed by Landauer's principle. Biological systems provide natural examples of demon-like behavior. Molecular motors in cells perform work by coupling to chemical gradients and using conformational changes to bias otherwise random thermal motion. These systems effectively sort high and low energy states to maintain cellular organization, but they require continuous energy input from metabolic processes to operate. The Demon paradox has influenced understanding of computation limits and energy efficiency in information processing. As electronic devices become smaller and more sophisticated, they approach fundamental thermodynamic limits on energy efficiency. The principle suggests minimum energy costs for performing computations, which become increasingly relevant as devices shrink toward molecular scales. Reversible computing represents one approach to circumventing Landauer's limit by avoiding information erasure. In reversible computation, every operation can be undone, preserving all information throughout the calculation. While theoretically possible, reversible computing faces practical challenges from error accumulation and the difficulty of constructing truly reversible logic gates. The Demon also connects to broader questions about the arrow of time and temporal asymmetry in physics. The Demon's operation relies on correlations between past measurements and future actions. The thermodynamic cost of maintaining these correlations contributes to the universe's overall entropy increase and helps explain why complex organized systems can exist within the broader context of thermodynamic equilibrium. Error correction and information reliability add additional layers to the Demon analysis. Real information processing systems must cope with errors and noise that can corrupt stored information. Error correction protocols require additional memory and processing overhead, further increasing the thermodynamic cost of reliable information processing. Modern research explores Demon-like systems in the context of stochastic thermodynamics, which studies fluctuations and rare events in small systems. These investigations reveal how information can be harvested from thermal fluctuations in systems far from equilibrium, while always respecting fundamental thermodynamic constraints when analyzed over appropriate timescales. The Demon paradox also relates to discussions of consciousness and the physical basis of observation. Some interpretations suggest that conscious observers play special roles in quantum measurement, potentially connecting the Demon's information processing to deeper questions about mind-matter interactions. However, mainstream physics explanations focus on purely physical aspects of information processing and memory operations. Networks of communicating demons present additional complexities where multiple agents share and process information cooperatively. These scenarios explore how distributed information processing affects thermodynamic constraints and whether coordinated demon networks could achieve capabilities beyond individual demons. Game-theoretic aspects emerge when multiple demons compete for resources or optimization objectives. The resolution of Maxwell's Demon paradox represents a triumph of theoretical physics that connected previously disparate areas, including thermodynamics, information theory, and computation. The paradox forced physicists to recognize that information has physical reality and thermodynamic consequences, establishing foundations for modern understanding of computation, measurement, and biological information processing. Technological applications of demon-related principles appear in energy harvesting systems that extract work from environmental fluctuations. These devices use feedback control to bias random processes, enabling energy recovery from ambient vibrations, thermal gradients, or electromagnetic noise. While they cannot exceed fundamental thermodynamic limits, they can approach theoretical efficiency bounds under carefully controlled conditions. The Demon also provides a conceptual framework for understanding how living systems maintain organization despite thermodynamic tendencies toward disorder. Biological organisms act as sophisticated information processing systems that use genetic and metabolic machinery to sort, concentrate, and organize materials. The thermodynamic cost of this organization is paid through energy consumption and heat generation that increases environmental entropy, fluctuation. Theorems in modern statistical mechanics provide additional perspectives on daemon-like operations by quantifying rare events where small systems temporarily decrease their entropy. These theorems show that while entropy can decrease in finite systems over finite times, such decreases become exponentially unlikely for larger decreases or longer durations, maintaining overall consistency with thermodynamic principles. Maxwell's daemon ultimately taught physicists that information and energy are fundamentally linked aspects of physical reality. The daemon's apparent violation of thermodynamics dissolved once the informational costs of its operation were properly accounted for, revealing deep connections between computation, measurement, memory, and the thermodynamic arrow of time. This understanding continues to influence research into computation limits, biological information processing, and the physical foundations of information itself. Time crystals. Time crystals represent one of the most counterintuitive discoveries in modern physics, revealing systems that exhibit periodic motion in their ground state without any external energy input. These exotic phases of matter break temporal translational symmetry in the same way that ordinary crystals break spatial translational symmetry, creating structures that repeat not in space but in time. The discovery of time crystals challenged fundamental assumptions about equilibrium states and opened new frontiers in quantum many-body physics. The concept emerged from theoretical work by Nobel laureate Frank Wilczek in 2012, who wondered whether systems could exhibit spontaneous symmetry, breaking in the time dimension, analogous to the spatial symmetry, breaking observed in ordinary crystals. Regular crystals form when atoms arrange themselves in repeating patterns that break the continuous translational symmetry of space, creating discrete preferred locations. Wilczek proposed that similar symmetry breaking might occur in time, creating systems with preferred temporal intervals. Initially, many physicists were skeptical about the possibility of time crystals. The concept seemed to violate basic thermodynamic principles by suggesting that systems could exhibit periodic motion in their lowest energy states. If a system could move perpetually without energy input, it would appear to constitute a perpetual motion machine of the first kind, violating energy conservation. These concerns led to early arguments that true time crystals were impossible in equilibrium systems. The resolution came through understanding that time crystals don't violate energy conservation but rather represent non-equilibrium steady states that can exist under periodic driving. These discrete time crystals emerge in systems that are periodically driven at one frequency but respond with oscillations at a different frequency, typically half the driving frequency. This period doubling response creates stable, long-lived states that exhibit temporal order while dissipating energy to maintain their non-equilibrium condition. The first experimental realization of discrete time crystals was achieved using trapped ions in Paul traps. These experiments created chains of ions held in electromagnetic fields and subjected to periodic laser pulses that flipped the ion spins according to specific protocols. Under the right conditions, the ion spins exhibit collective oscillations that persist at half the driving frequency, even in the presence of disorder and interactions that should destroy such coherent behavior. Nuclear magnetic resonance systems provided another platform for time crystal realization. Researchers used networks of nuclear spins in diamond crystals containing nitrogen vacancy centers, subjecting them to carefully designed pulse sequences. These systems demonstrated robust time crystalline behavior that persisted even when experimental parameters were varied over wide ranges, suggesting that time crystals represent a new phase of matter rather than fine-tuned laboratory curiosities. The stability of time crystals relies on many-body localization, a quantum mechanical phenomenon where strong disorder prevents thermalization in interacting systems. In typical many-body quantum systems, interactions lead to thermalization, where local observables reach thermal equilibrium values and lose memory of initial conditions. Many-body localized systems resist this thermalization, maintaining quantum coherence and local memory over long time scales. Many-body localization acts as a protective mechanism that prevents time crystals from heating up and reaching thermal equilibrium. Without this protection, the periodic driving would eventually pump energy into the system until all temporal order is destroyed by thermal fluctuations. Localization maintains the delicate balance between order and disorder necessary for stable time crystalline behavior. The discovery revealed that time crystals exist as a discrete time translation symmetry breaking phase in driven quantum systems. Just as ferromagnets spontaneously break spatial rotation symmetry by developing a preferred magnetic direction, time crystals spontaneously break discrete time translation symmetry by responding to periodic driving with a different period. This symmetry breaking is spontaneous because it occurs even when the driving protocol preserves the relevant time translation symmetry. Floquet theory provides the mathematical framework for understanding periodically driven quantum systems and time crystals. This theory extends quantum mechanics to systems with time-periodic Hamiltonians, revealing how driving can stabilize exotic phases that don't exist in equilibrium. Floquet time crystals represent eigenmode solutions to the driven system that oscillate with twice the driving period, creating robust temporal order. The period doubling response that characterizes discrete time crystals emerges from the system's collective response to periodic driving. Individual components may respond chaotically or irregularly to the driving, but their collective behavior exhibits precise temporal periodicity. This collective phenomenon demonstrates how emergent properties can arise from complex many-body interactions, even in strongly disordered systems. Pre-thermalization plays a crucial role in time crystal stability by creating long-lived metastable states that resist thermalization on experimentally relevant timescales. Even in systems that are not perfectly many-body localized, pre-thermalization can extend the lifetime of time crystalline behavior far beyond naive expectations. This mechanism broadens the parameter ranges where time crystals can be observed and suggests they may be more robust than initially anticipated. Different classes of time crystals have been discovered beyond the original discrete time crystals. Continuous time crystals exhibit oscillations that persist without any external driving, though their existence in truly isolated systems remains controversial. Space-time crystals combine spatial and temporal periodicity, creating patterns that repeat in both space and time dimensions with potentially novel properties. Quantum time crystals represent a distinct category where quantum coherence and entanglement play essential roles in maintaining temporal order. These systems exhibit quantum correlations that persist over many driving periods, creating temporal patterns that have no classical analog. Understanding these quantum aspects requires sophisticated theoretical tools from quantum information theory and many-body quantum mechanics. The relationship between time crystals and thermalization has revealed deep connections between non-equilibrium physics and fundamental aspects of quantum mechanics. Time crystals exist in a realm between integrable systems that never thermalize and generic systems that rapidly reach thermal equilibrium. They represent a new category of quantum matter where partial thermalization creates stable, non-equilibrium phases. Experimental signatures of time crystals include long-range temporal correlations, period doubling responses to driving, and resilience to perturbations that would destroy conventional ordered states. These signatures must be distinguished from transient effects or trivial responses to driving, requiring careful analysis of the system's behavior over many driving cycles and under various parameter changes. Applications of time. Crystal physics are beginning to emerge in quantum sensing, quantum information processing, and precision metrology. The robust temporal correlations in time crystals could provide new platforms for quantum memories that store information in temporal patterns rather than spatial configurations. Their resistance to decoherence makes them potential candidates for quantum technologies operating in noisy environments. The study of time crystals has also advanced understanding of eigenstate thermalization hypothesis and its violations. This hypothesis explains how generic quantum systems reach thermal equilibrium through the properties of individual energy eigenstates. Time crystals and many-body localized systems represent important exceptions where eigenstate thermalization fails, leading to persistent non-thermal behavior. Disorder plays a paradoxical role in time crystals, simultaneously threatening their stability through decoherence while protecting them through localization. The interplay between disorder and interactions determines whether systems exhibit time crystalline behavior, complete localization, or thermalization. Understanding this balance remains an active area of research with implications for quantum technologies and fundamental physics. Theoretical work continues to explore the boundaries of time crystal existence and the conditions necessary for their stability. Different driving protocols, interaction strengths, and system geometries all influence time crystal formation and lifetime. These studies aim to identify universal principles governing time crystalline behavior and predict new types of temporal order. The connection between time crystals and other non-equilibrium phenomena has revealed unexpected relationships within condensed matter physics. Time crystals share features with driven dissipative systems, quantum scars, and other exotic phases that resist thermalization. These connections suggest that non-equilibrium quantum matter may be far richer than previously imagined. Criticisms and ongoing debates about time crystals focus on questions about their fundamental nature and the precise conditions for their existence. Some researchers argue about whether observed phenomena truly represent new phases of matter or are better understood as transient effects in driven systems. These debates reflect the novelty of the field and the challenges of establishing rigorous definitions for non-equilibrium phases. Machine learning approaches are increasingly used to identify and characterize time crystals in complex quantum systems. These techniques can detect temporal patterns and phase transitions that might be difficult to identify through conventional analysis, potentially revealing new types of time crystalline behavior in systems that are too complex for analytical treatment. The discovery of time crystals represents a paradigm shift in understanding non-equilibrium quantum matter and the possibilities for temporal organization in physical systems. By breaking time translation symmetry while maintaining stability, time crystals reveal new principles governing quantum many-body systems and expand the boundaries of what's possible in condensed matter physics. Their continued study promises to uncover additional surprises about the nature of time, order, and quantum mechanics in driven systems. Simulation hypothesis. The simulation hypothesis proposes that our perceived reality might be an artificial simulation, similar to a computer program running on some advanced computational system. This idea, while popularized in recent decades through science fiction and philosophical discourse, raises profound questions about the nature of existence, consciousness, and our ability to distinguish authentic reality from sophisticated imitation. The hypothesis intersects philosophy, computer science, and physics in ways that challenge our most basic assumptions about what it means to exist. The modern formulation of the simulation hypothesis gained prominence through philosopher Nick Bostrom's 2003 paper, which presented it as a trilemma rather than a definitive claim. Bostrom argued that at least one of three propositions must be true. Advanced civilizations almost never reach technological maturity. Technologically mature civilizations have little interest in running ancestor simulations, or we are almost certainly living in a computer simulation. This logical structure sidesteps the need to prove we are simulated, instead demonstrating that simulation is a likely outcome under reasonable assumptions about technological development. The technological foundation for the hypothesis rests on exponential growth in computational power and our increasing ability to create realistic virtual environments. Moore's law, which describes the doubling of transistor density approximately every 2 years, suggests that future computers could possess computational resources orders of magnitude greater than today's systems. If this trend continues, future civilizations might have enough processing power to simulate entire universes complete with conscious beings who believe they inhabit physical reality. Virtual reality technology provides a glimpse of how simulated environments might evolve. Current systems can create immersive visual and auditory experiences, while haptic feedback systems add tactile sensations. As these technologies advance, they approach the threshold where simulated experiences become indistinguishable from reality for the beings within them. Extrapolating this trend suggests that sufficiently advanced civilizations could create simulations so detailed that inhabitants would have no way to detect their artificial nature. The computational requirements for reality simulation present both challenges and possibilities. Simulating every atom in a human body would require enormous computational resources, but various optimization strategies could make such simulations feasible. The simulation might only render details when they are observed, similar to how video games only generate visible portions of virtual worlds. Quantum mechanics itself might provide natural compression, with the simulation computing probabilities rather than definite states, until measurement forces specific outcomes. Digital physics theories suggest that reality itself might be fundamentally computational. If the universe operates like a cellular automaton or quantum computer at its deepest level, then the distinction between real and simulated reality becomes meaningless. In this view, our universe might be indistinguishable from a simulation because both would be computational processes running on some form of information processing substrate. The ancestor simulation variant of the hypothesis proposes that advanced civilizations might run detailed historical simulations to study their past or provide experiences for their descendants. These simulations would recreate specific historical periods with inhabitants who believe they are living in the original timeline. If such simulations are common, the number of simulated beings could vastly outnumber beings in original reality, making simulation statistically likely for any given conscious observer. Consciousness represents a crucial challenge for simulation hypotheses. Creating artificial consciousness requires understanding how subjective experience emerges from physical processes. If consciousness is purely computational, then sufficiently complex simulations could indeed contain conscious beings with genuine subjective experiences. However, if consciousness requires specific physical substrates or quantum processes, then simulated beings might lack genuine awareness despite appearing conscious to external observers. The problem of other minds complicates any attempt to verify the simulation hypothesis through introspection. We cannot directly access other people's consciousness to confirm they are genuinely aware, rather than sophisticated behavioral imitations. This limitation means that even in a simulation we could not distinguish between other conscious beings and non-conscious, but behaviorally appropriate programs designed to maintain the illusion of a populated world. Potential evidence for the simulation hypothesis includes various anomalies and limitations that might reflect computational constraints. Some researchers point to quantum mechanics' apparent digital nature, with quantized energy levels and information limits that resemble pixelation in digital images. Others note that physical constants might represent parameters in a cosmic program, though these observations could equally well reflect fundamental features of reality rather than simulation artifacts. The fine-tuning problem in cosmology has been cited as potential evidence for simulation. The apparent precise calibration of physical constants that allow for complex structures and life might reflect intentional parameter selection by simulation designers rather than extraordinary cosmic coincidence. However, this argument faces the same explanatory challenges as design arguments in general, potentially pushing the mystery back without resolving it. Glitches in the matrix represent another category of potential evidence, including reports of déjà vu, apparent synchronicities, and claimed observations of reality glitches. However, these phenomena have well-established psychological and neurological explanations that don't require invoking simulated reality. The human brain's pattern recognition systems and memory processes naturally create experiences that might seem like simulation artifacts. Testing the simulation hypothesis faces fundamental methodological challenges. If a simulation is designed to be indistinguishable from reality, then by definition no test could reliably detect it. Any apparent evidence of simulation could be intentionally included by the simulators to maintain the illusion, or could reflect genuine features of non-simulated reality that happen to resemble what we might expect from simulation. The nested simulation problem adds additional complexity to the hypothesis. If we are in a simulation, our simulators might themselves be simulated beings, creating an infinite regress of simulated realities. This scenario would make it impossible to determine how many levels of simulation separate us from base reality, or whether base reality exists at all in any meaningful sense. Ethical implications of the simulation hypothesis raise troubling questions about the responsibilities of advanced civilizations toward simulated beings. If simulated beings can suffer, then running simulations containing suffering might be ethically problematic. Conversely, if simulated beings lack genuine consciousness, then their apparent suffering would be meaningless, though determining which case applies remains impossible from within the simulation. The existential impact of believing in simulation varies among individuals. Some find the hypothesis liberating, suggesting that perceived limitations and sufferings might be artificial constraints that could potentially be modified or transcended. Others find it troubling, undermining the significance of their experiences and relationships. Still others argue that the hypothesis makes no practical difference, since we must live according to our experienced reality, regardless of its ultimate nature. Resource limitations provide potential constraints on simulation scope and fidelity. Even advanced civilizations would face computational limits that might require trade-offs between simulation size, detail level, and duration. These constraints might create detectable signatures in the form of simplified physics at extreme scales, reduced complexity in unobserved regions, or other optimization artifacts. The anthropic principle intersects with simulation arguments in complex ways. If observers can only exist in realities compatible with their existence, then the apparent fine-tuning of our universe for life might simply reflect observational selection, rather than design or simulation. This principle could apply equally to simulated and non-simulated realities, providing no clear evidence for either scenario. Quantum mechanics presents both opportunities and challenges for simulation theory. The apparent randomness and observer-dependent nature of quantum measurements might reflect computational shortcuts in a simulated reality, with the simulation generating outcomes only when required. Alternatively, simulating genuine quantum mechanics might require quantum computers, potentially making universe simulation more challenging than classical approaches suggest. Recent developments in artificial intelligence and machine learning have renewed interest in simulation hypotheses by demonstrating rapid progress toward human-level performance in various cognitive tasks. If artificial consciousness becomes achievable, it would strengthen the plausibility of creating simulated beings who genuinely believe they exist in physical reality. The simulation hypothesis ultimately confronts us with fundamental questions about the nature of reality, knowledge, and existence that have challenged philosophers for millennia. Whether or not we live in a simulation, grappling with the hypothesis illuminates important issues about consciousness, computation, and the relationship between appearance and reality. The hypothesis serves as a modern variation on ancient skeptical arguments about the possibility of knowledge and the reliability of experience. While the simulation hypothesis cannot be definitively proven or disproven, Its exploration advances our understanding of consciousness, computation, and the nature of reality itself. The hypothesis encourages careful thinking about what we can truly know about our existence and what assumptions we make about the world around us. Whether we inhabit base reality or an advanced simulation, the experiences and relationships that constitute our lives retain their immediate significance and meaning for us as conscious beings navigating existence.